Hello there and welcome to Life Beyond Seen, a quiet little corner where curiosity slows down, familiar things are looked at from unusual angles, and science is explored in a way that hopefully lets your mind relax while still learning something interesting. Some people listen while winding down in the evening, some while travelling, others while simply letting their thoughts drift for a while. And wherever you happen to be right now, it is genuinely nice to have you here. Tonight's gentle exploration centres on a place many people think they already understand. Lakes, calm water, scenic shorelines, summer holidays, maybe a dock, maybe a small boat, maybe a childhood memory of skipping stones or watching sunsets reflected on smooth fresh water. But not all lakes behave the way those quiet mental pictures suggest. There is a group of lakes in North America so large, so complex and sometimes so unpredictable that sailors, meteorologists, rescue teams and shipping captains often talk about them with the same respect usually reserved for oceans. These are the Great Lakes, and despite being inland freshwater, they can at times be more dangerous than the open sea. It sounds slightly counterintuitive at first. Oceans are vast, deep and famously stormy. Lakes by comparison seem contained and manageable. Yet the Great Lakes regularly produce conditions that surprise even experienced mariners. Sudden weather shifts, steep waves, intense cold water, heavy shipping traffic, and deceptively familiar surroundings all combine into something that looks peaceful from shore, but demands serious caution once you're out on the water. Before we ease further into this, there is something I always enjoy hearing. Where are you listening from right now? And what does the environment around you feel like at this moment? Some people listen late at night when everything is quiet. Others tune in during early morning routines or while commuting. It creates an interesting contrast, talking about massive inland lakes while listeners are scattered across cities, countryside, coastlines and time zones, each person arriving at this same audio moment from very different surroundings. And if you happen to find this kind of slow exploration calming, informative, or just a pleasant background for winding down, a like or subscription is always appreciated. It helps this small space reach other people who enjoy relaxed science and thoughtful storytelling. No pressure, of course, just a gentle mention. So let's settle in and begin looking at why these lakes, which often appear so approachable, have built a reputation that commands respect from professionals who spend their lives on the water. The Great Lakes consist of 5 massive bodies of fresh water: Superior, Michigan, Huron, Erie and Ontario. Together they hold about 1/5 of the world's surface freshwater supply. That alone hints at their scale. Lake Superior, the largest, contains more water than all the other Great Lakes combined and is large enough to generate its own weather patterns. When you look at a map, it becomes clear that these lakes resemble inland seas more than typical lakes. Their shorelines stretch for thousands of kilometres, storms can travel long distances uninterrupted, and visibility across open water often shows nothing but horizon. Yet because they are lakes, many people subconsciously treat them as safer. There is a psychological effect at work. Lakes are often associated with recreation, cottages, fishing trips, and weekend boating. Oceans, on the other hand, carry an established reputation for danger. Sharks, hurricanes, vast distances, strong tides. The mental categories influence behaviour. People may take fewer precautions on a lake simply because it feels familiar and enclosed. Freshwater also behaves slightly differently from saltwater in ways that matter for safety. The buoyancy difference is subtle, but real. Saltwater helps you float a bit more easily. Freshwater provides less natural lift, which can make swimming more tiring, especially in rough conditions. It is not dramatic enough to notice casually, but in emergencies every physical factor becomes significant. Temperature is another critical piece. Oceans, especially near populated coasts, often maintain relatively stable temperatures compared to inland freshwater. The Great Lakes, particularly Superior, remain extremely cold for much of the year. Even in summer, deeper water temperatures can be shockingly low. Cold water shock is one of the most underestimated risks. Sudden immersion in cold fresh water can trigger involuntary gasping, rapid breathing, and loss of muscle control within minutes. People who are strong swimmers in pools or warm coastal water may find themselves overwhelmed quickly. Then there is the issue of weather speed. Ocean storms usually develop over long distances and attract extensively. Meteorological systems affecting the Great Lakes can form quickly because of temperature contrasts between land and water. A calm morning can shift into dangerous waves by afternoon. Experienced boaters often emphasize checking forecasts repeatedly, rather than relying on one earlier report. Wave behaviour on these lakes also deserves attention. Because the lakes are large but still enclosed, waves tend to be shorter in wavelength and steeper than many ocean swells. That means boats encounter choppier conditions with less time between crests. Even large vessels can experience heavy pitching. Smaller craft, including recreational boats, can become unstable quickly if operators are not prepared. Visibility changes present another layer. Fog forms frequently due to temperature differences between water and air. It can arrive quickly and reduce navigation visibility to a few meters. Unlike open ocean navigation, where there may be more room to maneuver away from hazards, the Great Lakes often combine reduced visibility with nearby shorelines, shipping channels, and infrastructure. Commercial shipping is actually a major factor that surprises people unfamiliar with the region. Massive cargo vessels known as lake freighters regularly transport iron ore, grain, coal, and other materials across these waters. Some are over 300 meters long. Their size, limited maneuverability, and the constrained channels of certain lake passages create situations where smaller recreational boats must remain alert. Collisions are rare, but the potential consequences are serious. History adds further context. The Great Lakes region contains thousands of documented shipwrecks. Some are centuries old. Others occurred within modern times despite advanced navigation technology. Sudden storms, structural stress from steep waves, ice hazards, and navigation errors have all contributed. These wrecks are studied not only for historical interest, but also for improving safety understanding. Ice itself is another seasonal dimension that differs from most ocean environments. Winter brings partial or sometimes extensive ice cover. While this can reduce wave formation temporarily, it introduces hazards such as shifting ice sheets, hidden openings, and difficult rescue conditions. Seasonal transitions between frozen and open water create unpredictable edges that must be treated carefully. Geography shapes risk as well. Certain shoreline areas, particularly along Lake Superior, are known for rocky coasts and limited safe harbours. If weather deteriorates quickly, reaching shelter may take longer than expected. Ocean coastlines often have established port infrastructure spaced at predictable intervals, whereas some lake stretches remain relatively remote. There is also the factor of overconfidence rooted in familiarity. Many residents live near these lakes for years. Familiar landscapes can reduce perceived risk. Someone who would never venture casually into the open ocean might take a small boat far offshore on a lake because land still feels conceptually close, even when it is not practically reachable. Emergency response times vary widely. Near major cities, rescue services are efficient and well equipped. In remote northern stretches, particularly on Lake Superior, response distances can be significant. Weather conditions that create emergencies also complicate rescue efforts. All of this contributes to a layered understanding. The Great Lakes are not inherently hostile, just as oceans are not inherently dangerous all the time. But they combine ocean-scale physical characteristics with lake-scale psychological familiarity. That combination leads to unique risk patterns. People who work regularly on these waters often emphasize respect rather than fear. Preparation, awareness of weather, appropriate equipment, flotation devices, communication tools, and realistic trip planning dramatically reduce danger. Education has improved outcomes over decades. Still, unexpected incidents continue to occur, usually involving rapid weather change, cold exposure, or navigation challenges. Another interesting aspect is how these lakes influence regional climate. Large water bodies store heat and release it slowly. This affects snowfall patterns, fog formation, and storm intensity near shorelines. Residents often become accustomed to these seasonal rhythms without always connecting them to safety implications on the water itself. As conversations about water safety expand globally, the Great Lakes frequently appear as case studies. They demonstrate how inland freshwater systems can produce conditions comparable to oceans while maintaining a public image of recreational tranquility. Understanding that contrast helps inform broader water safety education, and as we continue moving through this exploration, it becomes increasingly useful to look more closely at how these lakes behave physically, why their scale matters so much, and how the absence of salt does not reduce their power. The next part naturally leans into that idea, examining how freshwater seas develop ocean-like characteristics and why size alone begins to change the entire safety equation. When people picture a lake, the image is usually small enough that the opposite shore remains visible, waves are gentle and weather changes feel manageable. That mental picture works well for many lakes around the world, but it does not translate well to the Great Lakes. These bodies of water operate on a scale that shifts them into something closer to inland seas, even though they are technically fresh water. Understanding why they behave this way begins with size, depth, fetch distance, and the complex interaction between atmosphere and water surface. Scale changes everything in fluid systems. Lake Superior alone covers more than 82,000 square kilometres. That is larger than many entire countries. When wind moves across such a large uninterrupted surface, it has enough distance, known as fetch, to transfer substantial energy into the water. Small lakes limit wave formation because wind crosses them quickly. On the Great Lakes, wind can blow for hundreds of kilometres without obstruction. That sustained energy transfer produces waves comparable to coastal ocean conditions, sometimes exceeding 6 metres in height during strong storms. Depth adds another important factor. Many smaller lakes are shallow, which limits wave energy storage and temperature stability. Several Great Lakes, especially Superior and Michigan, contain deep basins that behave more like ocean shelves. Deep water retains cold temperatures, moderates seasonal warming, and supports large internal circulation systems. These circulation patterns influence currents, fog formation, nutrient distribution, and ice development. All of these influence how conditions evolve over time. Freshwater density also plays a subtle but measurable role. Freshwater is slightly less dense than salt water. That affects buoyancy, thermal layering, and mixing patterns. In saltwater oceans, salinity gradients combine with temperature gradients to produce stable stratification layers. The Great Lakes rely mostly on temperature differences for layering. During summer, warm surface water sits above colder deep water, limiting vertical mixing. When autumn cooling arrives, the surface layer cools rapidly, becomes denser, and sinks, creating seasonal turnover. This turnover can redistribute nutrients, oxygen, and temperature profiles in ways that influence weather interaction and visibility conditions. Weather interaction is where the ocean-like behaviour becomes particularly noticeable. Large water bodies absorb solar energy slowly and release it slowly. This moderates nearby air temperatures and can generate localised weather systems. Lake effect snow, common around these lakes, happens when cold air moves across relatively warmer lake water, picking up moisture that later falls as heavy snow downwind. Similar processes drive fog formation, localised storms, and rapid atmospheric pressure changes. Storm development on the Great Lakes can be especially abrupt because of temperature contrasts between surrounding land masses and water surfaces. Land heats and cools faster than water. This differential creates pressure gradients that can strengthen wind quickly. A calm morning can shift into strong afternoon winds capable of producing hazardous waves. Unlike oceans, where large-scale storm systems are tracked over vast distances, lake storms sometimes intensify locally with shorter warning periods. Wave structure on these lakes deserves careful attention because it differs from typical ocean swells. Ocean waves often travel long distances from their generating storms, creating smoother, longer period swells. Great Lakes waves are frequently wind-driven locally, producing shorter wavelengths and steeper profiles. These steep waves hit vessels with more frequent vertical motion, increasing structural stress and making navigation physically demanding. Smaller recreational boats can experience rapid pitching that reduces stability and increases risk of swamping. Currents exist here as well, though they are less widely discussed than ocean currents. Wind-driven surface currents can develop quickly, especially in narrow connecting channels such as the Straits of Mackinac or the Detroit River system. Temperature-driven density currents also occur seasonally. These currents may not appear dramatic visually, but they can influence drift patterns, swimmer safety, and navigation planning. Visibility conditions further blur the line between lake and ocean environments. Fog forms frequently due to temperature differences between air and water. Warm, humid air passing over colder water condenses into dense fog banks. These can develop rapidly and reduce visibility to near zero. Mariners must rely on radar, GPS navigation, and sound signals, much like ocean navigation protocols. Ice cycles present another distinctive element. Unlike most oceans, which rarely freeze except near polar regions, several Great Lakes experience seasonal ice cover. Ice reduces wave formation temporarily, but introduces hazards such as shifting flows, pressure ridges, and hidden open water gaps. Ice breakup periods can be particularly dangerous because stable-looking surfaces may weaken quickly. Commercial shipping adapts using ice-breaking vessels, but recreational users sometimes underestimate changing ice conditions. Human infrastructure around these lakes also mirrors coastal environments. Major ports handle bulk cargo shipping comparable to ocean trade routes. Iron ore, grain, petroleum products, and manufactured goods move regularly across the lakes. Large freighters known as lakers operate specifically for these conditions. Their design reflects the steep wave patterns, freshwater corrosion differences, and lock systems connecting lakes at different elevations. Lock systems themselves demonstrate the ocean-scale nature of these lakes. Elevation differences between lakes require massive engineering work such as the Soo locks, connecting Lake Superior and Lake Huron. These locks accommodate ships hundreds of meters long. Their existence signals that the lakes function as an integrated maritime network rather than isolated recreational water bodies. Biological ecosystems also resemble marine-scale complexity. Fisheries management involves large-scale population monitoring, invasive species control, and cross-border regulatory cooperation between the United States and Canada. Zebra mussels, sea lampreys, and other invasive organisms have significantly altered ecological balance. These ecological shifts influence water clarity, nutrient cycling, and even wave reflection characteristics along shorelines. Coastal erosion patterns around the Great Lakes parallel ocean coast processes. Strong storms generate wave energy capable of reshaping beaches, cliffs, and dunes. Seasonal water level fluctuations amplify these effects. Property owners along shorelines often implement erosion control measures similar to ocean coastal engineering, including breakwaters, revetments, and vegetation stabilization. Psychological perception remains one of the most interesting aspects. Because these lakes lack salt water, tides, and ocean branding, many people instinctively categorize them as safer. Yet statistically, maritime incidents occur regularly. Search and rescue operations on the Great Lakes follow protocols similar to coastal ocean rescues, involving helicopters, specialized vessels, and coordinated communication networks. Temperature gradients influence survival time significantly. Cold water immersion is often more severe here than in many coastal oceans at similar latitudes because fresh water can cool faster seasonally. Hypothermia risk rises quickly, sometimes within minutes. Proper flotation devices, thermal protection suits for professionals, and emergency preparedness training reflect this reality. Navigation technology has advanced safety considerably. Modern vessels rely on GPS positioning, electronic charts, weather radar, and automated identification systems that track nearby ships. These technologies reduce collision risk and improve route planning. Still, technology supplements rather than replaces situational awareness. Rapid weather shifts still require human judgment. Recreational activity remains popular. Sailing, fishing, kayaking, and tourism thrive around the lakes. Public education campaigns emphasize weather awareness, flotation device use, and cold water preparedness. Many incidents involve experienced individuals who underestimated conditions rather than novices lacking basic knowledge. Research institutions study these lakes extensively. Limnology, the science of inland waters, treats the Great Lakes as unique laboratories for large-scale freshwater processes. Findings influence global freshwater management strategies, climate modelling, and environmental protection policies. Cross-border governance between the United States and Canada adds another dimension. Water quality agreements, pollution control initiatives, shipping regulations, and fisheries management require international coordination. This governance structure reflects recognition that the lakes function as shared maritime environments. From a broader perspective, the Great Lakes illustrate how classification labels can shape risk perception. Calling something a lake suggests calmness. Calling it an inland sea would likely change public expectations. Terminology influences preparation, caution levels, and safety behaviour. Meteorological forecasting continues improving, offering better storm prediction accuracy. Satellite monitoring, buoy networks, and advanced modelling provide earlier warnings. Even so, localised effects remain challenging to predict perfectly. Mariners still rely on continuous observation and contingency planning. As understanding deepens, it becomes clearer that these freshwater seas combine physical characteristics of oceans with accessibility that invites widespread recreational use. That combination makes education essential, respecting the scale, monitoring weather closely, preparing for cold water, and recognizing the limitations of familiarity all contribute to safer interaction. And once the scale comparison settles in, the next aspect that naturally follows is how sheer size alone generates hazards that people often associate only with oceans. The discussion gradually shifts toward the consequences of that scale, particularly how large uninterrupted water surfaces create risks that smaller lakes simply cannot produce. Once the idea settles in that the Great Lakes behave more like inland seas than typical lakes, the next thing that becomes important is simply how big they are. Size alone changes how water behaves, how weather interacts with it, and how humans experience risk on it. Salt content has very little to do with danger compared with sheer surface area, depth, and distance between shores. When you place enough fresh water in one basin, the physical rules that govern oceans begin to show up almost automatically. A useful starting point is visibility. On smaller lakes, you almost always see land in multiple directions. That visual reference provides orientation, comfort, and practical navigation cues. On the Great Lakes, there are many areas where you can travel far enough from shore that nothing but horizon surrounds you. That psychological shift matters. When people no longer see land, decision-making tends to change. Some become overly cautious, others underestimate how far they have travelled because the environment still feels like a lake rather than an ocean. Either way, orientation becomes dependent on instruments rather than sight. Distance also affects response time. If a boat develops mechanical trouble on a small lake, shore is usually reachable quickly. On the Great Lakes, distances can stretch to tens or even hundreds of kilometres. Rescue vessels, helicopters, or nearby ships may need significant time to arrive. That delay means preparedness becomes critical. Life jackets, communication equipment, navigation tools, and weather awareness all matter more when help cannot appear quickly. Wave development ties directly into this scale. Wind energy builds gradually as it crosses water. The longer that uninterrupted distance, the more energy transfers into wave motion. Meteorologists call this fetch length. On oceans, fetch can extend thousands of kilometres. The Great Lakes provide fetch distances long enough to generate substantial wave heights, particularly during strong storm systems. These waves may not match the largest ocean swells, but they often become steep, closely spaced, and unpredictable. That combination is challenging for vessels because it produces rapid pitching rather than smooth rolling motion. Boat design considerations reflect this. Commercial freighters operating on these lakes resemble ocean-going ships in hull strength, navigation systems, and crew training. Recreational boaters sometimes assume that lake boating requires less preparation than coastal boating, yet conditions can demand similar seamanship skills. Weather monitoring, route planning, and contingency preparation are standard practice among experienced operators. Depth contributes further complications. Deep water stores cold temperatures year-round. Surface layers warm during summer, but below a relatively shallow thermocline, water remains cold. This temperature structure influences both weather and safety. Cold water immersion risk remains high even during warm months. People often judge water safety by air temperature, but deep lakes maintain cold reserves that influence surface conditions. Thermal inertia also shapes storm intensity. Large water bodies moderate surrounding air temperature, creating pressure differences that drive wind systems. Rapid changes in air temperature relative to water temperature can intensify winds unexpectedly. These winds then feed wave development, visibility changes, and navigational challenges. The chain reaction begins with size and heat capacity rather than salt content. Another effect of scale involves shoreline complexity. The Great Lakes have extensive coastlines with bays, peninsulas, cliffs, sandy beaches, wetlands, and urban ports. This varied geography influences local wind patterns. Wind accelerates around headlands, creates turbulence near cliffs, and channels through narrow passages. Localized conditions may differ significantly from regional forecasts. Mariners who rely solely on broad weather reports sometimes encounter stronger winds than expected due to shoreline effects. Water level fluctuations represent another large-scale factor. Seasonal precipitation, evaporation, and inflow from tributary rivers cause measurable changes in lake levels. These fluctuations affect harbour accessibility, coastal erosion, and wave impact on infrastructure. Unlike tidal oceans, these level changes occur over weeks or months rather than hours, yet they still influence navigation planning and shoreline safety. Commercial shipping adds to the scale conversation. Massive cargo vessels navigate these lakes regularly. Some exceed 300 metres in length and carry tens of thousands of tons of cargo. Their presence creates unique hazards. Large ships produce significant wakes, require wide turning radii, and cannot stop quickly. Recreational boaters sharing the same waters must remain aware of shipping lanes and maintain safe distances. Navigation systems reflect the seriousness of these waters. Buoy networks, lighthouses, radar beacons, and electronic chart systems resemble coastal maritime infrastructure. These aids help vessels maintain safe courses through channels, avoid shoals, and navigate in poor visibility. Their presence signals recognition that these lakes require professional maritime standards. Weather unpredictability increases when large water surfaces interact with complex atmospheric systems. Storm fronts moving across continental North America encounter the lakes and sometimes intensify. The temperature contrast between land and water alters air stability, moisture content, and wind patterns. Rapid storm formation can surprise people expecting slower changes typical of smaller lakes. Fog formation also ties to scale. Large cold water surfaces cool moist air efficiently, leading to condensation. Dense fog banks can develop quickly and persist for hours. Navigation in fog requires radar, sound signals, and disciplined watchkeeping. Without these, orientation becomes difficult even for experienced boaters. Human perception continues playing a role. Calling something a lake suggests boundaries and containment, That perception may reduce caution. People often assume they can always return to shore quickly. In reality, distances may require hours of travel, especially in adverse weather. Recognizing that scale helps adjust expectations and encourages preparation. Cold water survival statistics highlight another consequence: immersion times. Before hypothermia onset depend heavily on water temperature, body condition, flotation support, and protective clothing. Because these lakes remain cold for much of the year, survival windows can be short. Emergency preparedness training emphasizes wearing flotation devices, carrying signaling equipment, and planning routes conservatively. Research vessels studying these lakes operate much like oceanographic ships. They deploy buoys, conduct depth surveys, sample water chemistry, and monitor ecological changes. Scientific investment reflects recognition that these lakes influence regional climate, water supply, transportation, and environmental health. Cross-border governance reinforces this scale perspective. The United States and Canada share responsibility for water quality, fisheries management, pollution control, and shipping regulation. International agreements guide environmental protection efforts. Few lakes globally require such extensive multinational coordination. Economic importance further underscores their ocean-like role. Bulk cargo transportation across the lake supports industries ranging from steel production to agriculture. Ports such as Duluth, Chicago, Detroit and Toronto function as major logistical hubs. Maritime safety regulations reflect the economic stakes involved. Climate change research increasingly focuses on these lakes. Changing ice cover patterns, shifting precipitation levels, and temperature trends influence water levels, storm intensity, and ecological balance. Long-term monitoring helps anticipate future safety considerations for both shipping and recreation. Recreational culture around the lakes remains strong. Sailing regattas, fishing tournaments, kayaking expeditions, and tourism attract millions annually. Education campaigns emphasize respecting conditions, checking weather frequently, and understanding cold water risks. Experienced local communities often share practical knowledge that complements official guidance. Search and rescue operations illustrate the seriousness of these environments. Coast Guard units, marine police, and volunteer organizations maintain readiness similar to coastal regions. Helicopters, fast response boats, and coordinated communication networks support emergency response. Training scenarios often assume ocean-level hazards. Technological advances continue improving safety. Satellite weather monitoring, real-time buoy data, smartphone navigation apps, and automated distress signaling devices give modern boaters more information than previous generations. Still, technology cannot replace judgment. Equipment failure or unexpected weather remains possible. Understanding scale without salt ultimately means recognizing that water physics depends primarily on size, depth, and energy input. Salinity influences buoyancy and corrosion, but does not determine wave power, weather interaction, or rescue complexity. Large freshwater bodies behave according to the same physical laws governing oceans, and as attention shifts from sheer size to how weather behaves over these vast surfaces, the next natural area of exploration becomes storms themselves, not just their strength, but how quickly they form, how unexpectedly they intensify, and why sailors often describe Great Lakes storms as some of the fastest changing conditions they encounter. Once the scale of the Great Lakes starts to make sense, the next thing that tends to catch people off guard is how quickly weather can change there. Many sailors who are comfortable on coastal waters often mention that these lakes have a reputation for fast-building storms. It is not that storms on the oceans are slow or gentle, but oceans usually allow weather systems to develop over long distances where tracking is easier. On the Great Lakes, the interaction between land, water, and atmosphere can compress that process into a shorter window, sometimes leaving very little time between calm conditions and genuinely hazardous ones. A key factor is temperature contrast. Land heats up and cools down much faster than water. During warm months, surrounding land areas can become significantly hotter than the lake surface. That temperature difference affects air pressure. Warm air rises over land, cooler air sits above the lake, and the pressure imbalance encourages air movement. When these gradients sharpen, wind can strengthen rapidly. What begins as a light breeze during a calm morning can evolve into sustained strong winds by afternoon, especially when combined with incoming weather fronts. Cold fronts moving across North America frequently interact with the lakes in ways that intensify local conditions. When a cold air mass slides over relatively warmer lake water, instability increases. Rising air currents strengthen, moisture evaporates from the surface, and cloud development accelerates. Thunderstorms sometimes form quickly in these situations. Sailors have reported conditions shifting from clear skies to heavy rain, lightning, and strong winds within an hour or two. Humidity plays a role as well. Large freshwater surfaces provide significant evaporation. Moist air moving over the lakes can contribute to cloud formation, even when surrounding land appears relatively clear. This moisture source sometimes feeds localized storm development that was not fully predicted by broader regional forecasts. Weather models continue improving, but small-scale lake interactions remain challenging to predict perfectly. Wind direction shifts also matter. Because the lakes are large yet enclosed by land masses, winds can funnel along certain geographic orientations. Shorelines, peninsulas, and nearby terrain influence airflow patterns. When wind aligns with the long axis of a lake, fetch increases quickly, producing higher waves in a relatively short time. A change in wind direction of even a few degrees can significantly alter wave conditions. Pressure changes often provide early clues, though casual boaters do not always monitor barometric trends. A falling barometer suggests approaching unsettled weather. Experienced mariners sometimes check pressure readings regularly, especially during seasons known for rapid weather transitions. Combining pressure data with visual observation of cloud development improves situational awareness. Cloud structure itself offers hints. Cumulonimbus clouds, characterized by vertical development and anvil-shaped tops, often signal thunderstorms. On the Great Lakes, these can appear relatively quickly because of the moisture and temperature contrasts already present. Rapid cloud growth accompanied by darkening skies usually indicates strengthening atmospheric instability. Lightning risk deserves attention. Open water provides little shelter, and lightning strikes over lakes occur regularly during storm seasons. Boaters caught far from shore face increased exposure. Monitoring forecasts, carrying weather alert radios, and maintaining awareness of cloud development all help reduce risk. Visibility deterioration accompanies many sudden storms. Heavy rain reduces sight distance, while wind-driven spray further obscures navigation. Combined with choppy waves, these factors complicate steering and situational awareness. Radar and GPS navigation systems help professionals, but smaller recreational vessels may rely more heavily on visual cues. Temperature drops can also be abrupt. A passing storm front sometimes brings cooler air masses that lower surface air temperature quickly. That drop increases hypothermia risk for anyone exposed to wind, rain, or spray. Even without immersion, prolonged exposure to cold wind and wet conditions reduces physical endurance. Seasonal timing influences storm patterns. Late summer and early autumn often produce particularly dynamic conditions. Warm lake water meets cooler incoming air masses, strengthening atmospheric instability. Some historically severe Great Lakes storms occurred during these transitional seasons when temperature contrasts were greatest. Winter storms present a different set of challenges. Strong winds interacting with cold water can produce freezing spray. Ice accumulation on vessel decks, railings, and superstructures increases weight and destabilizes ships. Commercial vessels operating in winter conditions implement specific safety procedures to manage icing risk. Forecast reliability has improved dramatically with satellite monitoring, advanced modelling, and buoy data networks. Real-time wave height measurements, wind speed data, and temperature readings provide valuable situational awareness. Still, Microscale weather changes remain difficult to predict precisely, especially near complex shorelines. Professional mariners often emphasize continuous monitoring rather than relying on a single forecast check. Weather apps, marine radio broadcasts, and onboard instruments all contribute to a dynamic picture. Recreational boaters increasingly have access to similar information through smartphones and portable devices, but consistent attention remains essential. Historical records contain many accounts of sudden Great Lakes storms causing maritime incidents. Some involved large commercial vessels, others smaller recreational craft. Analysis of these incidents often highlights rapid weather deterioration combined with delayed response decisions. Awareness of how quickly conditions can shift helps inform safer behaviour. Human psychology sometimes delays response to changing weather. People naturally prefer to continue planned activities rather than alter course. When conditions worsen gradually, that tendency can lead to late decision-making. On the Great Lakes, where changes may accelerate quickly, early caution often proves beneficial. Communication infrastructure supports safety efforts. Marine radio channels provide weather updates, navigational warnings, and distress coordination. Coast Guard units, harbour authorities, and weather services collaborate to distribute timely information. Familiarity with communication protocols improves response effectiveness. Another subtle factor involves wave reflection. When strong winds push waves toward shorelines with cliffs or harbour structures, reflected wave energy interacts with incoming waves. This interference produces chaotic wave patterns that are difficult to predict visually. Mariners approaching shore during storms must account for these complex interactions. Commercial shipping schedules adapt to weather conditions. Large vessels sometimes delay departures or alter routes based on forecasted storms. Shipping companies invest heavily in meteorological analysis because cargo safety, crew welfare, and economic considerations all depend on accurate risk assessment. Recreational boating communities increasingly emphasize safety training. Courses cover weather interpretation, emergency procedures, cold water awareness, and communication skills. Participation in such training correlates with reduced incident rates. Education helps bridge the gap between perception of lakes as recreational spaces and recognition of their maritime scale. Technological aids continue expanding. Automatic identification systems allow vessels to track each other electronically. Weather routing software suggests safer paths around developing storms. Portable emergency beacons enable rapid distress signalling even far from shore. These tools enhance safety but require familiarity and proper maintenance. Climate trends may influence future storm behaviour. Research suggests changes in temperature patterns, ice cover duration, and precipitation cycles could alter storm frequency or intensity. Ongoing monitoring helps scientists anticipate how these changes might affect maritime safety on the lakes. Respect for local knowledge remains valuable. Long-time residents, commercial fishermen, and experienced sailors often recognize subtle environmental cues that complement formal forecasts. Observing cloud movement, water texture, wind scent, and bird behavior sometimes provides early hints of changing conditions. As the discussion of sudden storm settles in, attention naturally shifts toward another major factor that makes these waters particularly unforgiving. Weather may initiate danger, but the water itself, especially its temperature, plays an equally important role. The cold nature of Great Lakes water introduces risks that persist even during calm conditions, and understanding that aspect becomes the next logical step in appreciating why these inland seas command such consistent respect. When people look out across the Great Lakes on a calm day, the surface can appear surprisingly peaceful. Sunlight reflects gently, the horizon looks stable, and there may be very little visible motion. That visual calm often leads to assumptions about safety. Yet one of the most serious risks connected with these waters has very little to do with waves or storms. It sits quietly below the surface, and it remains present even on the most tranquil days. That risk is cold water shock. a physiological response that happens when the body suddenly encounters very cold water. Many people associate dangerous cold water only with winter conditions. The reality on the Great Lakes is different. Because of their depth and volume, these lakes retain cold temperatures year-round. Surface layers warm during summer, but deeper water stays cold, and mixing events can bring that cold water upward unexpectedly. Even in late summer, temperatures in some areas may be low enough to trigger significant physiological stress. Cold water shock begins immediately upon sudden immersion. The first reaction is often an involuntary gasp reflex. This happens within seconds and can be dangerous if the person's head is underwater at that moment. Water inhalation risk rises sharply during this initial stage. Simultaneously, breathing rate increases dramatically. People may hyperventilate, losing control of breathing rhythm. Panic sometimes follows, especially if the person was not expecting the immersion. Heart rate and blood pressure also change rapidly. The body attempts to protect core temperature by constricting blood vessels near the skin. This sudden cardiovascular stress can be dangerous, particularly for individuals with underlying heart conditions. Even otherwise healthy individuals may experience dizziness or disorientation during this phase. Muscle function changes quickly as well. Cold exposure reduces muscle efficiency. Hands lose dexterity first. Tasks such as fastening flotation devices, gripping boat edges, or operating communication equipment become harder. Within minutes, swimming strength declines. People who consider themselves strong swimmers in warm water sometimes underestimate how quickly cold water reduces endurance. Hypothermia develops over a longer time frame, but cold water shock itself can incapacitate someone before hypothermia becomes the primary concern. Survival discussions often focus on hypothermia timelines, yet the first few minutes after immersion frequently determine outcomes. Staying afloat, controlling breathing, and maintaining orientation are critical during this initial phase. Flotation devices significantly improve survival chances. Life jackets help keep airways above water during involuntary breathing reactions. They also reduce the need for active swimming, conserving energy, and helping maintain body heat. Safety campaigns around the Great Lakes consistently emphasize wearing flotation devices rather than simply carrying them on board. Clothing choices matter too. Regular clothing provides limited insulation when wet. Specialized cold water immersion suits used by professional mariners offer thermal protection and buoyancy. Recreational users rarely wear full immersion suits, but layered clothing, waterproof outer garments, and personal flotation devices together improve outcomes compared with minimal clothing. Water temperature perception can be misleading. Air temperature strongly influences expectations. A warm, sunny day encourages assumptions of comfortable water, yet deep lakes warm slowly. Surface readings may appear moderate while deeper water remains cold enough to cause shock. Sudden immersion through a fall or boat capsize exposes the body to those colder layers immediately. Wind conditions influence thermal stress as well. After immersion, wind accelerates heat loss through evaporation. Wet clothing combined with strong wind speeds increases cooling rates, even if air temperature seems mild. Remaining out of the water but soaked and exposed still poses risk. Seasonal transitions produce particularly deceptive conditions. Spring often combines warming air with still cold water. Recreational activity increases during this time, but water temperatures lag behind seasonal expectations. Many cold water incidents occur during spring boating and fishing seasons. Alcohol consumption sometimes contributes indirectly. Alcohol impairs judgment, reduces awareness of cold exposure symptoms, and affects balance. It also alters blood vessel responses, potentially accelerating heat loss. Safety education programs frequently highlight these combined risks. Cold water shock education has expanded over recent decades. Public awareness campaigns, boating safety courses, and Coastal Guard outreach emphasize recognizing early symptoms. Simple practices such as testing water temperature before extended activity, wearing flotation devices consistently, and informing others of travel plans all improve safety. Professional maritime operations incorporate strict cold water protocols. Commercial crews conduct safety drills, maintain immersion suits, and use thermal protective gear when necessary. Emergency response training often includes cold water survival techniques, such as heat conservation postures and group huddling strategies. Scientific research continues exploring physiological responses to cold immersion. Studies measure breathing patterns, cardiovascular reactions, muscle function, and cognitive performance under controlled conditions. Findings inform updated safety recommendations and equipment design. Psychological factors influence outcomes as well. Panic responses increase oxygen consumption, accelerate fatigue, and impair decision-making. Training that emphasizes controlled breathing and calm response helps individuals manage initial shock more effectively. Communication equipment plays an important role. Waterproof radios, emergency locator beacons, and mobile communication devices improve rescue coordination. Rapid distress signaling shortens response times, which can be critical given the limited survival window in cold water. Rescue operations on the Great Lakes frequently involve helicopters due to distance from shore. Cold water conditions complicate both rescue and post-rescue care. Medical teams often treat hypothermia, respiratory complications, and shock symptoms simultaneously. Boat design features sometimes incorporate safety considerations related to cold water. Self-righting vessels, accessible reboarding ladders, and enclosed cabins improve survival prospects after accidental immersion. Recreational boaters increasingly look for such features when selecting equipment. Public beaches and swimming areas maintain safety infrastructure such as lifeguards, temperature monitoring, and warning signage. Even so, individuals venturing beyond supervised areas must rely on personal preparation and awareness. Environmental conditions can change quickly. Upwelling events, where deeper cold water rises to the surface, occasionally lower surface temperatures unexpectedly. These events result from wind patterns and water circulation changes. Swimmers and boaters may notice sudden temperature differences without obvious visual cues. Long-term climate trends influence lake temperature patterns. Warmer average air temperatures may alter ice cover duration and seasonal warming rates. However, deep water thermal inertia means cold exposure risk remains significant despite broader climate changes. Understanding cold water shock ultimately reinforces a broader theme. Danger does not always present itself dramatically. Calm water, clear skies, and warm air can coexist with physiological risks below the surface. Awareness, preparation, and consistent safety practices help manage those risks effectively. And once the hidden nature of cold water becomes clear, another closely related aspect begins to emerge. Many people instinctively believe lakes are safer than oceans simply because they are lakes. That perception itself shapes behaviour, and examining why freshwater environments sometimes feel deceptively safe becomes the next natural direction for this exploration. Once cold water risk becomes clear, another layer begins to make sense, and that layer has less to do with physics and more to do with human perception. Many people grow up around lakes. Family holidays, fishing trips, summer swimming, small boats tied to wooden docks. All of those images create a sense of familiarity. Oceans, by contrast, often carry a reputation for power and unpredictability. People hear about hurricanes, strong tides, large predators, and vast distances. That reputation naturally encourages caution. Lakes rarely receive that same psychological framing, even when they are large enough to behave like seas. This perception gap influences behaviour in subtle ways. When people feel comfortable, they often prepare less. Safety equipment may be present but not worn. Weather checks may happen once rather than continuously. Distance from shore may feel smaller than it actually is. None of this is reckless in intention. It usually comes from experience with smaller lakes where those assumptions hold true. The difficulty appears when those habits carry over to environments like the Great Lakes, where conditions operate on a completely different scale. Freshwater also lacks some obvious warning signs people associate with oceans. There are no tides of significant scale on the Great Lakes, at least not the dramatic tidal cycles familiar along coastlines. Without tides, water levels seem stable from hour to hour. That stability can create the impression of predictability, even though wind-driven changes in wave height and currents can still become intense. Because tides are absent, some people subconsciously assume other ocean hazards are absent too, even when they are not. Another perception factor involves salinity. Salt water feels different on the skin. It tastes distinct. The smell of the ocean often signals its presence before it even comes into view. Fresh water does not provide those sensory cues. It feels neutral and familiar. That sensory neutrality contributes to the sense that the environment is less extreme. Yet from a physical standpoint, wind energy, wave formation, visibility conditions, and cold exposure risk operate independently of salt content. Visibility itself plays a role in shaping comfort levels. Many coastal oceans are associated with murkier water, surf noise, and dramatic horizons. Some areas of the Great Lakes, especially when calm, appear glassy and quiet. Clear fresh water, particularly in northern sections, can appear inviting and manageable. That calm visual presentation sometimes hides underlying hazards, such as sudden drop-offs, cold layers, or changing weather patterns. Cultural narratives reinforce the perception. Lakes often appear in advertising as relaxing vacation destinations. Cabin culture, shoreline communities, and recreational boating imagery emphasize tranquility. Oceans, meanwhile, are frequently portrayed in media as powerful or dangerous. Films, documentaries, and news coverage highlight storms and maritime rescues. Those repeated narratives influence how people assess risk before they even approach the water. Experience levels contribute too. People living near the Great Lakes may spend years around them without encountering severe conditions personally. Long periods of calm reinforce confidence. That confidence is understandable, but it can reduce attention to rare but serious events. Maritime safety studies often show that familiarity sometimes correlates with lower perceived risk, even when objective hazards remain unchanged. Swimming expectations also differ. Ocean swimmers often expect currents, waves, and cooler temperatures. Lake swimmers sometimes expect still water and warmer temperatures. When conditions differ from expectations, response time slows. Cold shock, wave action, or unexpected currents can feel surprising rather than anticipated. Freshwater buoyancy differences, though modest, matter in extended exposure situations. Saltwater supports flotation slightly better. That extra buoyancy can make a difference when someone is fatigued. In freshwater, maintaining flotation may require slightly more effort. People unaware of this difference may tire sooner than expected. Another deceptive element involves shoreline proximity. On many Great Lakes beaches, land remains visible from considerable distances offshore. Seeing land can create a sense of security, even when returning to shore would require significant time or energy. Visual closeness does not equal practical accessibility, especially in rough conditions or cold water. Weather forecasting also interacts with perception. Coastal regions often emphasize marine forecasts prominently. Inland regions sometimes focus more on land-based weather. Great Lakes forecasts exist and are detailed, but recreational users may not always consult marine-specific reports. Differences between land forecasts and marine forecasts can be substantial. Infrastructure differences contribute subtly. Ocean harbours often include visible maritime signals such as large breakwaters, busy shipping traffic, and coastal warning systems. Some Great Lakes shorelines appear more residential or recreational. That quieter infrastructure can reduce perceived seriousness, even though commercial shipping operates extensively in the region. Historical awareness varies as well. Many people know famous ocean maritime disasters. Fewer are aware of the large number of shipwrecks in the Great Lakes. The region holds thousands of documented wreck sites. Awareness of that history sometimes changes perception, but many recreational users remain unfamiliar with it. Education campaigns increasingly address these perception gaps. Boating safety organisations emphasise that large lakes require ocean-level respect. Messaging encourages consistent flotation device use, weather monitoring, and conservative trip planning. Outreach targets both residents and visitors unfamiliar with the lake's scale. Technology can both help and hinder perception. GPS navigation, smartphone weather apps, and digital communication provide valuable safety tools. At the same time, reliance on technology sometimes creates overconfidence. Devices fail, batteries deplete, signals drop. Experienced mariners typically combine technological aids with traditional observation skills. Cold water awareness specifically challenges the safe lake assumption. Many incidents involve individuals who would have prepared differently if entering ocean water, but assumed a lake environment would be warmer. Education emphasizing actual temperature data, rather than seasonal expectations, helps counter this. Group dynamics influence risk decisions. When multiple people share a perception of safety, caution may decrease collectively. Social reinforcement of relaxed attitudes sometimes delays precautionary actions. Conversely, safety-oriented group culture improves outcomes significantly. Local knowledge remains valuable. Residents familiar with specific areas often recognize subtle weather cues, current patterns, and seasonal changes. Visitors lacking that knowledge benefit from consulting local expertise, marina staff, or experienced boaters before venturing far from shore. Emergency response infrastructure exists throughout the region, including Coast Guard stations, marine police units, and volunteer rescue organisations. Their presence reflects recognition that freshwater does not eliminate maritime risk. Response planning often mirrors coastal operations in equipment and training. Environmental stewardship also connects with safety. Pollution monitoring, invasive species control, and shoreline management all influence water conditions. Clear water does not automatically mean safe water. Ecological factors sometimes affect visibility, navigation hazards, and water chemistry. Economic activity reinforces the lake's maritime identity. Major shipping routes transport industrial materials across international borders. Commercial fishermen operate year-round. Research vessels conduct scientific studies. These activities treat the lakes as working seas rather than recreational ponds. Psychological adaptation takes time. Individuals who transition from smaller lakes to the Great Lakes often report an adjustment period. Respect for distance, weather variability, and cold exposure grows with experience. Formal training accelerates that adjustment. Safety culture continues evolving. Educational outreach, technological improvements, and community awareness campaigns contribute to gradual perception shifts. The goal is not to create fear, but to align perception with reality so preparation matches conditions. And once the idea of deceptive familiarity settles in, attention naturally moves toward how the water itself behaves when wind energy increases. Waves on the Great Lakes often look different from ocean waves, not necessarily larger but steeper and closer together. Understanding those wave mechanics helps explain why navigation can become challenging faster than many people expect. Once the idea settles in that the Great Lakes are not simply oversized versions of small recreational lakes, the next thing that starts to matter is how the water actually moves when wind begins transferring energy into it. Waves are not just surface decoration. They are physical energy patterns shaped by wind speed, wind duration, fetch distance, water depth, shoreline geometry, and atmospheric pressure. On these lakes, those factors combine in a way that produces wave behaviour that often surprises even experienced sailors, especially those more accustomed to coastal ocean conditions. Ocean waves frequently travel long distances from the storms that generated them. These are known as swell waves. They tend to have longer wavelengths and smoother motion. A boat riding ocean swell may experience gradual lifting and lowering rather than abrupt vertical motion. That does not make oceans safe, but the wave rhythm is often more predictable. The Great Lakes, by contrast, tend to generate locally driven wind waves. Because the fetch, while large, is still limited compared with oceans, the waves have shorter spacing. That shorter wavelength creates steeper profiles. Steep waves place particular stress on vessels. When a boat meets a steep wave head-on, the bow may rise sharply, then drop quickly into the trough. This repeated pitching motion strains hull structures, affects balance, and increases fatigue for anyone on board. Large commercial vessels are built with this in mind, yet even they can experience heavy structural loads during strong storms. Smaller recreational boats feel these effects much more intensely. Wave period, the time between successive wave crests, is a key measurement. Ocean swell may have periods of 10 to 20 seconds or more. On the Great Lakes, periods often drop to a few seconds in storm conditions. That rapid sequence leaves less recovery time between impacts. Operators must constantly adjust throttle, steering angle and vessel orientation to maintain stability. Cross seas represent another challenge. Because wind direction can shift quickly, and shoreline reflections can interfere with incoming waves, boats sometimes encounter waves arriving from multiple angles simultaneously. These intersecting patterns create irregular motion that is harder to anticipate. A vessel may roll sideways while also pitching forward, complicating steering and increasing risk of water coming aboard. Shoreline reflections contribute significantly in certain areas. Rocky coasts, harbour walls and breakwaters reflect wave energy back toward open water. Incoming waves meeting reflected waves generate confused seas. Even moderate winds can produce unexpectedly chaotic conditions near such structures. Navigators approaching shore during deteriorating weather must account for these interactions. Depth transitions also influence wave shape. As waves move into shallower water, their speed decreases while height often increases. This process, called shoaling, steepens waves further. Near coastal shallows of the Great Lakes, this effect can intensify already steep waves, creating braking conditions that challenge navigation. Breaking waves carry additional hazards. When a wave crest becomes unstable and collapses, it can send significant water over decks. Smaller boats may ship water faster than bilge pumps can remove it. Maintaining appropriate heading relative to waves becomes critical. Professional seamanship training emphasizes wave angle management specifically for these situations. Wind speed alone does not determine wave severity. Duration matters. Sustained strong winds over several hours allow waves to grow progressively. Sudden gusts create short-term disturbances, but persistent wind builds larger systems. Monitoring both wind speed and forecast duration helps anticipate conditions. Atmospheric pressure gradients influence wind strength. Rapidly falling pressure often signals strengthening storms. Mariners watching barometric trends sometimes gain early warning before waves become visibly severe. Combining instrument data with visual observation improves readiness. Water temperature interacts with wave behavior indirectly. Cold water affects air density above the surface, which in turn influences wind friction characteristics. Seasonal temperature contrasts sometimes enhance wind energy transfer efficiency. While subtle, these effects contribute to seasonal wave pattern differences. Navigation strategies adjust accordingly. Commercial vessels sometimes alter course to take waves at safer angles rather than shortest distance routes. Recreational boaters learn similar techniques. Heading directly into steep waves may reduce rolling, but increases pitching stress. Taking waves at slight angles balances motion but requires skillful steering. Speed management becomes essential. Excessive speed into steep waves risks structural impact damage. Too little speed may reduce steering control. Finding an appropriate balance requires experience, observation, and sometimes trial adjustments as conditions evolve. Human endurance factors into safety as well. Continuous exposure to steep wave motion induces fatigue. Balance maintenance requires muscular effort. Reduced concentration increases risk of navigational error. Long transits during rough conditions demand rest planning and crew rotation where possible. Seasickness is another practical consideration. Short, irregular wave motion often triggers motion sickness more quickly than long, predictable swell. Impaired crew performance due to seasickness can affect decision-making and reaction time. Preparation sometimes includes medication, hydration, and strategic positioning within vessels. Equipment design reflects these realities. Lake freighters feature reinforced hulls, high bows, and specific ballast systems to handle steep waves. Recreational vessels designed for Great Lakes use often include deeper hull shapes and stronger structural elements compared with boats intended only for sheltered waters. Safety equipment placement also adapts. Handholds, lifelines, anti-slip decking, and secure storage reduce accident risk during rough motion. Properly secured cargo and gear prevent shifting weight that could destabilize vessels. Search and rescue operations must account for wave behavior. Helicopter hoist operations become more complex in steep seas. Rescue vessels approach distressed boats cautiously to avoid collision from unpredictable wave motion. Training exercises frequently simulate such conditions. Technological aids assist navigation in rough water. Radar helps maintain situational awareness when spray reduces visibility. GPS charting systems assist course holding. Automatic identification systems provide awareness of nearby commercial vessels that may be harder to see amid wave spray. Weather buoys positioned throughout the lakes provide real-time wave height, period, and wind data. Mariners increasingly consult these before departure and during voyages. Access to live data improves decision-making compared with relying solely on forecasts. Recreational education programs emphasize wave awareness. Courses teach recognizing whitecap formation stages, interpreting water texture changes, and adjusting course early. Early response prevents escalation into emergency situations. Historical incidents often highlight wave mechanics. Several documented shipwrecks occurred when steep waves overwhelmed vessels not structurally prepared, or when navigational decisions underestimated wave severity. Investigation reports frequently mention shortwave periods as contributing factors. Public perception sometimes equates wave danger with wave height alone. Height matters, but steepness and period often determine handling difficulty. 2-meter waves with short periods can be more challenging than higher waves with long periods. Shoreline users experience wave effects differently. Strong waves contribute to coastal erosion, structural damage, and hazardous swimming conditions. Rip currents sometimes develop where wave energy concentrates, posing risk even to strong swimmers. Climate variability may influence future wave patterns. Changing wind regimes, temperature gradients, and ice cover duration could alter seasonal wave characteristics. Research institutions continue monitoring trends to refine safety recommendations. Understanding wave mechanics ultimately reinforces the broader message. These freshwater seas generate physical conditions comparable to coastal environments, sometimes with additional complexities. Preparation, respect for changing conditions, and continuous observation remain key elements of safe navigation. And as wave behavior becomes clearer, another factor naturally follows. Even when waves build and conditions deteriorate, escaping to safety is not always straightforward. Shorelines are not uniformly accessible, harbours are not always nearby, and planning exit routes becomes an essential part of operating safely on these vast inland waters. Once wave behavior starts making sense, another practical reality gradually comes into focus, and that reality involves geography. It might seem intuitive that being on a lake always means land is relatively close, and therefore safety is readily available. On smaller lakes, that assumption often holds true. On the Great Lakes, however, shoreline proximity does not automatically translate into accessible refuge. Distance, coastline shape, infrastructure availability, weather interaction with terrain, and even underwater hazards all influence whether reaching shore is actually a safe option. Distance alone is the first factor. Although the Great Lakes are enclosed by land, their surface areas are so large that vessels can easily travel far enough offshore that returning quickly becomes difficult. Lake Superior, for example, is wide enough that crossing it can require many hours even under favourable conditions. If weather deteriorates midway through such a crossing, the nearest shoreline may still be far away. That distance complicates both self-rescue and organised rescue response. Shoreline type matters just as much as distance. Not all shores provide safe landing conditions. Many stretches consist of rocky cliffs, steep drop-offs, marshlands, or densely vegetated areas without docking facilities. Attempting to land in rough conditions along such terrain can cause vessel damage or personal injury. Waves breaking against rocks amplify impact forces, sometimes making offshore conditions safer than attempting an uncontrolled landing. Harbour distribution varies across the lakes. Some regions have frequent marinas, ports, or protected bays. Others, particularly remote northern stretches, may offer long intervals without formal harbour infrastructure. Mariners planning routes often mark potential refugee locations in advance, recognising that not every visible shoreline represents a viable shelter option. Weather interacts strongly with shoreline geometry. Wind blowing towards shore increases wave steepness as water depth decreases. This shoaling effect can create breaking waves near coastlines even when offshore waves remain manageable. In such cases, approaching land may increase rather than reduce risk. Experienced sailors sometimes hold position offshore until conditions stabilise rather than attempting immediate landfall. Currents complicate approach decisions as well. Wind-driven surface currents can push vessels toward hazardous areas faster than anticipated. Narrow channels between islands or peninsulas sometimes accelerate water flow. Approaching shore without accounting for these currents can result in loss of steering control, especially for smaller craft. Visibility plays another role. Fog banks frequently form along temperature transition zones near shorelines. Land may be physically close yet visually obscured. Navigational markers, buoys, and harbour entrances can become difficult to locate without electronic navigation aids. Reduced visibility combined with steep waves creates a challenging environment for approach manoeuvres. Underwater hazards remain less visible but equally important. Shoals, reefs, submerged rocks, and sandbars exist throughout the Great Lakes. Nautical charts identify many of these hazards, but visual detection is unreliable, particularly in rough water or low visibility. Grounding incidents sometimes occur when vessels attempt hurried shoreline approaches during deteriorating weather. Human psychology again influences decision-making. The instinct to head for land during difficulty is strong. That instinct often works in many environments, but on these lakes, careful evaluation is required. A distant protected harbour may offer better safety than a nearby exposed coastline. Planning before departure helps avoid rushed decisions. Seasonal conditions further affect shoreline accessibility. Ice accumulation during winter months alters harbour entrances and shoreline characteristics. Spring thaw introduces floating debris such as logs or ice remnants that can obstruct approach routes. Autumn storms sometimes coincide with reduced daylight hours, making visual navigation harder. Infrastructure quality varies widely. Major urban ports provide extensive docking facilities, breakwaters, navigation lighting, and rescue services. Remote areas may offer only natural coves without constructed protection. Even when natural shelter exists, entrance channels may be narrow or shallow, requiring precise navigation. Emergency response planning accounts for these geographic factors. Coast Guard units maintain knowledge of accessible landing points, helicopter hoist zones, and rescue staging areas. Response strategies often involve guiding distressed vessels towards specific safe locations, rather than nearest land indiscriminately. Commercial shipping illustrates structured route planning. Large freighters follow established shipping lanes designed to minimize grounding risk and optimize access to ports. Recreational boaters sometimes benefit from consulting similar route information, even when operating smaller vessels. Communication equipment becomes crucial when escape options are limited. Marine radios, Satellite communication devices and emergency beacons allow coordination with rescue services, even when immediate land access is unavailable. Prompt communication shortens response times. Navigation education emphasizes chart reading skills. Understanding bathymetry, shoreline contours, harbour locations and hazard markings helps mariners anticipate safe refuge options. Electronic chart plotters assist, but familiarity with underlying geography remains valuable. Local knowledge again provides an advantage. Residents familiar with specific coastlines often know protected coves, seasonal conditions and less obvious hazards. Visiting boaters sometimes consult local marina operators or experienced sailors before exploring unfamiliar sections. Environmental conservation zones occasionally restrict shoreline access. Protected wetlands, wildlife habitats, and conservation areas may limit docking or landing. Respecting these restrictions is important both legally and ecologically, but it also requires planning alternative refuge options. Coastal erosion affects harbour reliability over time. Changing sediment patterns alter depths and shoreline configurations. Updated charts and local advisories help account for these changes. Relying on outdated information increases risk. Search and rescue statistics reflect these complexities. Some incidents involve vessels damaged during attempted emergency landings, rather than during initial offshore difficulties. Training increasingly emphasizes evaluating all options rather than reflexively heading shoreward. Technological improvements assist route planning. Satellite imagery, real-time weather overlays, and digital chart updates enhance situational awareness. Still, reliance on technology alone is insufficient without interpretive judgment. Recreational safety campaigns encourage conservative trip planning, identifying multiple refuge points, monitoring weather continuously, and setting turnaround thresholds improves safety outcomes. Many experienced boaters adopt the practice of turning back earlier than strictly necessary. Psychological comfort sometimes returns once land becomes visible, even if conditions remain hazardous. Awareness of that psychological shift helps maintain objective decision-making. Visible land does not guarantee safety. Environmental conditions beyond weather also influence shoreline safety. Water level fluctuations affect harbour depth. Seasonal algae blooms may reduce water clarity, complicating hazard detection. Floating debris after storms introduces additional risks. International border considerations arise on certain lakes shared by multiple countries. Approaching shore may involve customs regulations or communication requirements. While emergencies override formalities, awareness simplifies coordination. All of these elements reinforce the central point. Shorelines around the Great Lakes do not automatically function as safe havens. Distance, terrain, weather interaction, infrastructure and human perception all shape whether landfall improves safety or introduces new hazards. And as geographic escape limitations become clearer, another closely related factor emerges. Even when shore access exists, visibility conditions sometimes deteriorate rapidly, especially with fog formation over large, cold freshwater surfaces. Understanding how visibility loss affects navigation naturally becomes the next part of the picture. Once shoreline access stops feeling like a guaranteed safety net, the next environmental factor that starts to matter is visibility. On the Great Lakes, visibility conditions can change in ways that feel gradual at first, almost subtle, until suddenly the horizon is gone. Fog is one of the most common reasons for that shift. It does not arrive with the drama of a thunderstorm or the obvious force of heavy wind. It often builds quietly, and that quietness is exactly what makes it dangerous. Fog formation over large freshwater bodies comes down mostly to temperature differences between air and water. The Great Lakes, especially the deeper northern sections, stay cold for much of the year. When warm, moist air moves across that colder surface, water vapour condenses into tiny droplets suspended in the air. Those droplets scatter light, reducing visibility sometimes to just a few meters. What looked like a wide-open landscape moments earlier can become visually featureless. That featureless quality matters psychologically as well as practically. Humans rely heavily on visual reference points for orientation. A visible shoreline, distant vessel, or even the sun's position helps maintain spatial awareness. When fog removes those cues, navigation becomes instrument-dependent. Without proper tools, disorientation happens quickly. People sometimes underestimate how fast orientation can degrade when visual references disappear. Depth perception also changes in fog. Objects appear farther away or closer than they actually are because the usual contrast cues are missing. A buoy, another boat, or a shoreline structure might emerge suddenly from the mist with little warning. Reaction time shrinks accordingly, increasing collision risk. Sound behaves differently in fog too. Moist air can carry sound farther, but it also scatters directionality. A ship's horn may be audible but difficult to locate precisely. Mariners often rely on standardized sound signals in reduced visibility conditions. Those signals help indicate vessel presence and movement when sight alone is insufficient. Navigation technology plays a critical role here. Radar systems allow detection of other vessels, shoreline features, and obstacles beyond visual range. GPS chart plotters help maintain course accuracy. Automatic identification systems broadcast vessel positions electronically. These technologies significantly reduce risk, but they require familiarity and proper calibration. Over-reliance without understanding limitations can create false confidence. Smaller recreational boats may not carry full radar systems. Portable GPS devices and smartphone navigation apps help, but battery life, signal reliability, and environmental exposure affect performance. Redundant navigation methods, including traditional compass use and chart familiarity, remain valuable. Fog rarely forms uniformly. Patches can develop unevenly, with clear zones adjacent to dense banks. Moving through such transitions requires constant awareness. Entering a dense fog patch unexpectedly can startle operators unprepared for sudden visibility loss. Temperature inversions sometimes intensify fog persistence. When warmer air sits above cooler air near the water surface, vertical mixing reduces. Fog droplets remain suspended longer. These inversions occur frequently during calm conditions following temperature shifts. Morning hours often see fog dissipate as sunlight warms surface air, but that process varies. Cloud cover, wind speed, and humidity levels all influence how quickly visibility improves. Planning early departures sometimes requires contingency planning for delayed visibility clearance. Evenings present another pattern. Cooling land temperatures after sunset can encourage fog development near shorelines. Boaters returning late in the day occasionally encounter deteriorating visibility conditions after previously clear outings. Shipping traffic increases complexity. Large commercial vessels operate continuously, regardless of visibility. They rely heavily on radar, established lanes, and communication protocols. Recreational boaters sharing those waters benefit from understanding shipping routes and maintaining radio monitoring during low visibility. Harbour approaches become particularly delicate in fog. Entrance markers, breakwaters, and navigation lights may not be visible until very close. Reduced speed, careful instrument monitoring, and communication with harbour authorities improve safety during such approaches. Psychological responses vary. Some individuals become overly cautious, reducing speed excessively or stopping entirely in unsafe areas. Others continue normal operations despite reduced visibility. Balanced decision-making involves reducing speed appropriately while maintaining steerage control and situational awareness. Training helps normalize these responses. Maritime courses often include fog navigation scenarios, emphasizing instrument interpretation, sound signaling, and lookout procedures. Familiarity reduces panic and improves reaction consistency. Weather forecasting services provide fog advisories based on temperature, humidity, and wind data. Monitoring these advisories before departure helps anticipate potential visibility issues. Real-time buoy data also indicate conditions conducive to fog formation. Environmental conditions unique to freshwater contribute as well. The absence of salt affects evaporation rates slightly, influencing local humidity patterns. Combined with the lake's depth and thermal inertia, these factors support frequent fog development compared with many inland water bodies. Historical maritime incidents on the Great Lakes frequently mention reduced visibility as a contributing factor. Collisions, groundings, and navigation errors often occurred when visual cues were limited. Investigation reports consistently highlight the importance of proper lookout procedures and instrument use. Wildlife activity sometimes increases in fog conditions. Birds resting on water surfaces or near shorelines may be harder to detect. Maintaining moderate speed helps avoid unexpected encounters. Lighting plays an interesting role. Bright onboard lights can reflect off fog droplets, reducing forward visibility further. Adjusting lighting appropriately helps maintain better external observation. Emergency signalling equipment becomes more important when visibility is limited. Audible distress signals, high visibility flags, and electronic beacons improve detection chances if assistance becomes necessary. Environmental acoustics also change. Wave sounds against shorelines or structures may seem amplified, sometimes providing indirect location clues. Experienced mariners sometimes use these auditory cues alongside instruments. Cold water interaction continues to matter. Fog often forms under conditions where water remains cold. Combined risks of reduced visibility and cold exposure reinforce the need for flotation devices and protective clothing even during calm conditions. Technological innovation continues improving fog navigation safety. Enhanced radar resolution, digital chart integration, and predictive weather modelling contribute to better situational awareness. Adoption among recreational users is gradually increasing. Community knowledge sharing helps as well. Local sailing clubs, marina operators, and experienced fishermen often exchange information about typical fog patterns in specific areas. These informal networks complement official forecasts. Understanding fog as a routine environmental feature rather than an unusual event helps normalize preparation. Carrying appropriate equipment, monitoring forecasts, and maintaining conservative operating practices reduce risk significantly. And once visibility challenges become clear, another factor begins to stand out. Even in reduced visibility, large commercial vessels continue operating across these lakes, following established shipping corridors. Their size, speed, and limited maneuverability introduce another layer of complexity, especially for smaller recreational craft sharing the same waters. Once visibility challenges enter the picture, another element naturally becomes part of the conversation, and that is the steady movement of commercial shipping across the Great Lakes. These waters are not only recreational spaces, they function as major transportation corridors linking industrial regions, agricultural centres, and international trade routes. Massive cargo vessels operate here daily, often year-round except during the harshest ice seasons. Their presence adds complexity that many first-time visitors do not fully anticipate. Great Lakes cargo ships, commonly called lakers, are specifically designed for these inland seas. Some stretch more than 300 metres in length, roughly the size of ocean-going bulk carriers. They transport iron ore, coal, limestone, grain, petroleum products, and manufactured goods. Their cargo capacity supports industries throughout North America. Because rail and road transport alone cannot efficiently handle those volumes, waterborne shipping remains essential. The scale of these ships influences how they move. Large vessels have significant momentum. Even at moderate speeds, stopping distances can extend for several kilometres. Turning radii are also wide. A freighter cannot manoeuvre quickly to avoid smaller boats that unexpectedly cross its path. From the perspective of a recreational boater, this means maintaining distance is not simply courteous, it is necessary for safety. Shipping lanes exist across much of the Great Lakes. These routes optimize depth, avoid underwater hazards, and provide efficient connections between ports. Charts mark these corridors clearly. Professional mariners follow them closely. Recreational users benefit from knowing where these lanes run, especially when crossing open water where visibility may already be limited. Narrow connecting channels create additional concentration points. The Detroit River, St. Clair River, St. Mary's River, and various canal systems link the lakes together. These waterways function like maritime highways. Large vessels passing through them operate under strict navigation rules. Smaller craft entering these channels must remain particularly vigilant. Locks play a major role in this system. The Soo locks, for example, allow ships to bypass elevation differences between Lake Superior and the lower lakes. Watching a large freighter pass through a lock highlights how integrated these lakes are as a commercial network. During lock approaches, vessel maneuverability is reduced further, and surrounding traffic coordination becomes essential. Visibility conditions amplify shipping complexity. In fog, heavy rain, or nighttime operations, large ships rely on radar, electronic identification systems, and communication protocols. Smaller vessels without equivalent equipment can be harder for ship crews to detect. Maintaining radio contact on designated marine channels helps bridge that gap. Wake generation from large ships deserves attention too. Although lakers typically move at moderate speeds, their displacement creates substantial wakes. These waves propagate outward and may persist long after the ship passes. Smaller boats encountering those wakes can experience abrupt motion changes, especially in already rough conditions. Propeller wash introduces another localized hazard. Large ship propellers move enormous volumes of water. Close proximity risks include strong currents capable of destabilizing small craft. Maintaining safe lateral distance prevents unintended interaction with these forces. Acoustic signaling remains part of maritime practice. Ship horns communicate presence, course intentions, or restricted visibility warnings. Understanding these signals helps smaller vessel operators interpret nearby traffic behaviour. Marine safety courses often include instruction on standard horn signals. Lighting patterns on large vessels convey information as well. Navigation lights indicate direction of travel, vessel size category, and operational status. Recognizing these patterns helps recreational boaters anticipate ship movement, particularly at night. Communication protocols support coordination. Marine VHF radio channels designated for bridge-to-bridge communication allow vessels to clarify intentions. Listening to these channels provides situational awareness even when direct communication is unnecessary. Commercial crews undergo extensive training. Navigation officers study meteorology, hydrodynamics, electronic systems, and emergency procedures. Their operational mindset prioritizes predictability and safety. Unexpected behavior from smaller craft creates operational challenges for them. Economic stakes reinforce adherence to safety protocols. Cargo shipments represent significant financial value. Delays, accidents, or environmental incidents carry substantial costs. Shipping companies invest heavily in risk mitigation. Environmental protection regulations shape shipping practices. Ballast water management, emission controls, and spill prevention measures aim to protect freshwater ecosystems. Compliance requires monitoring equipment and procedural discipline. Historical shipping records show the importance of these routes. Industrial development around the Great Lakes grew partly because reliable water transport enabled efficient movement of raw materials. Ports such as Duluth, Chicago, Detroit, Cleveland, and Toronto developed into major economic centres. Recreational boating growth has paralleled urban expansion. More people access these waters for leisure. Shared usage increases the need for awareness between commercial and recreational operators. Search and rescue planning incorporates shipping traffic patterns. Large vessels sometimes assist in rescue operations when nearby. International maritime tradition emphasizes mutual assistance at sea, and that extends to these lakes. technological evolution continues shaping shipping. Modern lakers use advanced navigation software, satellite communication, and automated monitoring systems. These tools enhance efficiency but still rely on skilled human oversight. Ice navigation, during winter, introduces additional shipping considerations. Icebreakers maintain channels for essential cargo transport. Coordination between icebreakers and cargo ships ensures safe passage through partially frozen waters. Public awareness campaigns often highlight safe crossing practices. Recreational boaters are encouraged to cross shipping lanes at right angles, minimize time spent within lanes, and avoid unpredictable maneuvers. Environmental conditions sometimes require shipping adjustments. Severe storms, heavy fog, or ice accumulation may prompt route changes or temporary port holds. Commercial scheduling includes contingency planning for such events. International cooperation remains central. The United States and Canada jointly regulate many aspects of Great Lakes shipping. Shared safety standards, communication systems, and environmental protections support consistent operations. From a broader perspective, these shipping corridors transform the lakes into functioning maritime highways. The term freshwater highway reflects both economic importance and operational complexity. Understanding the presence of large vessels reinforces a wider theme. These lakes combine recreational accessibility with industrial-scale maritime activity. That combination requires awareness, preparation, and respect from all water users. And once the reality of shared waterways becomes clear, attention naturally shifts toward water movement itself closer to shore. Even without ships, wind and wave interactions can create powerful currents, especially near beaches, piers, and breakwaters. Those currents introduce another set of risks that are often underestimated because they are less visible than waves or vessels. Once the presence of commercial shipping becomes part of the picture, it is easy to assume the greatest hazards lie far offshore. Yet some of the most dangerous water movement on the Great Lakes actually occurs very close to shore. This often surprises visitors because beaches and nearshore areas tend to feel safer. People expect gradual depth changes, manageable waves, and easy access back to land. In reality, certain shoreline conditions create strong currents, capable of pulling swimmers or small craft away from safety faster than most expect. Rip currents are one of the primary examples. Although often associated with ocean beaches, they occur on large lakes as well. When waves break along a shoreline, water piles up near the beach. That water must return to the open lake somehow. If the shoreline is uniform, the return flow spreads out gently. But when variations exist, such as sandbars, channels, or man-made structures, water funnels into concentrated streams moving away from shore. Those concentrated flows form rip currents. Unlike waves, rip currents are not always visually dramatic. They may appear as darker patches of water, areas with fewer breaking waves, or regions where floating debris moves steadily offshore. Without training, swimmers often interpret these calmer-looking zones as safer entry points. That misinterpretation contributes to many incidents. Rip current speed varies. Some move slowly enough for strong swimmers to manage. Others accelerate significantly, especially during storms or strong onshore winds. Even experienced swimmers may struggle against a fast-moving rip current because the instinctive reaction is to swim directly back toward shore. Swimming against the current quickly leads to exhaustion. Education emphasizes a different response, floating to conserve energy, signaling for help, and swimming parallel to shore rather than directly against the current usually provides safer outcomes. Once outside the narrow current channel, returning to shore becomes easier. Structural currents represent a related but distinct hazard. Human-built features such as piers, breakwaters, jetties, and harbour entrances alter natural water flow. Waves striking these structures reflect and redirect energy. Water may accelerate around edges or through gaps, creating strong localized currents. These currents can pull swimmers toward structures where waves increase impact risk. Boat operators must also account for structural currents. Approaching harbours during strong wave conditions sometimes involves navigating cross currents near breakwaters. Smaller craft may experience sudden lateral movement if operators underestimate these forces. Seasonal water level changes influence current strength. Higher water levels sometimes reduce sandbar prominence, altering rip current formation patterns. Lower levels expose additional underwater features that channel returning water differently. Regularly updated local information helps track these shifts. Wind direction remains a dominant factor. Persistent onshore winds increase wave-breaking intensity, which in turn increases the volume of water needing offshore return. That amplification strengthens rip currents. Monitoring wind forecast provides early clues about potential current risk. Temperature gradients occasionally contribute indirectly. Cold water near shore combined with warmer air can influence local wind patterns, which then affect wave generation. While temperature alone does not create rip currents, it shapes the environmental context. Visibility conditions complicate detection. Fog, rain, or glare from sunlight on water reduce the ability to spot subtle current indicators. Lifeguards trained to recognize rip patterns sometimes rely on elevated observation points to improve detection accuracy. Public beaches around the Great Lakes increasingly include warning flag systems. Coloured flags indicate current water safety conditions. Understanding these signals helps visitors make informed decisions. Ignoring posted advisories correlates strongly with incident reports. Rescue operations in rip current situations often involve lifeguards, marine patrol units, or nearby boaters. Quick recognition and response improve outcomes. Public awareness campaigns encourage bystanders to call for help rather than attempting untrained rescues, which sometimes create additional emergencies. Structural currents near shipping infrastructure require special caution. Harbour entrances designed for large vessels may produce strong water movement even in moderate weather. Recreational swimmers and boaters benefit from maintaining safe distances from these operational zones. Environmental factors such as algae blooms or turbidity sometimes obscure visual cues. Reduced water clarity makes it harder to identify channel patterns or debris movement associated with currents. Children and inexperienced swimmers face elevated risk. Lack of familiarity with current behaviour combined with panic responses increases vulnerability. Supervised swimming areas with lifeguards significantly reduce incident rates. Kayakers and paddleboard users also encounter these currents. Lightweight craft respond quickly to water movement. Wearing flotation devices and maintaining situational awareness improves safety for these activities. Wildlife behaviour occasionally provides indirect clues. Birds feeding along shore sometimes avoid strong current zones. Observing such patterns can supplement visual water assessment. Hydrodynamic research continues examining Great Lakes current behaviour. Universities deploy sensors and conduct modelling studies to improve predictive capability. Findings inform beach management policies and public safety messaging. Climate variability may influence current patterns over time. Changes in storm frequency, wind regimes, and water levels alter shoreline dynamics. Long-term monitoring helps identify evolving risk zones. Local knowledge again proves valuable. Residents familiar with specific beaches often recognize recurring current locations. Consulting local authorities or experienced community members before entering unfamiliar water adds an extra safety layer. Psychological comfort near shore remains a powerful influence. Many incidents occur within relatively short distances from land because individuals assume proximity equals safety. Awareness training emphasizes evaluating conditions objectively rather than relying solely on distance perception. Technological tools assist monitoring. Some beaches deploy current sensors, automated warning systems, and surveillance cameras. These tools enhance lifeguard effectiveness, but do not replace individual caution. Educational programs increasingly target tourists unfamiliar with Great Lakes conditions. Clear signage, multilingual materials, and outreach campaigns aim to reduce misunderstanding about freshwater current hazards. All of this reinforces a consistent message. Water movement near shore can be deceptively strong, even when waves appear modest. Respecting these forces improves safety outcomes for swimmers, boaters, and shoreline visitors alike. And once near-shore currents become part of the understanding, another seasonal dimension begins to matter. These lakes change dramatically across the year, shifting from open water to partial ice cover and back again. Those seasonal transitions introduce additional hazards that deserve careful attention. As currents near shore become easier to recognise as real hazards rather than rare exceptions, another factor begins to take shape, and that factor is time itself. Not time in the abstract sense, but the yearly cycle that reshapes the Great Lakes more dramatically than many other freshwater systems. These lakes do not remain static environments. They move through phases of open water, cooling, ice formation, thaw, and seasonal mixing, and each of those phases introduces its own safety considerations. What makes this especially important is how quickly some of these seasonal transitions can occur, sometimes catching even experienced lake users slightly off guard. Winter is often the first season people associate with danger on these lakes, and for understandable reasons. Ice formation begins as air temperatures drop and surface water cools. Because fresh water reaches maximum density just above freezing, surface water eventually becomes cold enough to freeze while deeper layers remain liquid. Ice cover does not form uniformly. Wind, currents, snowfall, and temperature fluctuations produce a constantly changing mosaic of thick ice, thin ice, open leads, and pressure ridges. From a distance, the surface may look solid and stable, but thickness can vary dramatically across short distances. Pressure ridges deserve particular attention. When large sheets of ice shift due to wind or thermal expansion, they can collide and pile upward or downward. Above the surface, ridges may look like uneven frozen waves. Below, jagged ice extensions can interfere with boat hulls or trap equipment. These formations change rapidly and are difficult to predict precisely. Commercial shipping operations adjust carefully during ice season. Icebreakers maintain navigable channels where essential cargo transport continues. These specialised vessels fracture ice sheets, creating pathways for freighters. Recreational boaters rarely operate in these conditions, but coastal residents sometimes venture onto frozen surfaces for activities like ice fishing or winter travel. Awareness of ice thickness variability becomes critical for personal safety. Ice thickness alone is not a reliable indicator of stability. Snow cover insulates ice, slowing thickening. Currents beneath the surface weaken ice from below. Temperature swings create freeze-thaw cycles that reduce structural integrity even when surface appearance seems unchanged. Safety guidelines typically recommend conservative thickness thresholds for walking, snowmobiles, and vehicles, but local variation always exists. Thaw cycles introduce a different set of challenges. As spring approaches, warming air temperatures gradually weaken ice sheets. Meltwater pools form on top, increasing weight and accelerating structural breakdown. Cracks widen, edges separate, and previously stable surfaces lose cohesion. People accustomed to winter conditions sometimes underestimate how quickly these changes occur. Spring also brings increased runoff from melting snow and seasonal rains. Rivers feeding the lakes carry debris, sediment, and sometimes floating ice fragments. This influx alters nearshore navigation conditions. Floating logs, branches, and ice chunks pose collision hazards, particularly for smaller vessels. Water temperature during early spring remains extremely cold, even as air temperatures rise. This period often sees increased recreational activity after winter confinement. Boaters eager to resume outings may encounter water temperatures still capable of inducing cold water shock. Air warmth can create misleading comfort cues, but water conditions lag behind seasonal expectations. Storm patterns during seasonal transitions often intensify. Temperature contrasts between warming land and still cold water strengthen atmospheric instability. Rapid weather shifts become more common, sometimes producing strong winds capable of generating steep waves within short time frames. Summer conditions appear comparatively stable, yet they introduce their own complexities. Thermal stratification develops as surface water warms while deeper water remains cold. This layering influences oxygen distribution, aquatic ecosystems, and occasionally surface water behaviour. Sudden storms can disrupt stratification temporarily, bringing colder water upward in localised upwelling events. Upwelling can cause noticeable temperature drops near shorelines. Swimmers and boaters sometimes encounter water significantly colder than expected. These events are not always forecast clearly because they depend on specific wind patterns and lake circulation dynamics. Summer also increases recreational density. Beaches, marinas, and open water routes become busier. Increased traffic raises collision risk, particularly in reduced visibility conditions or near popular shoreline destinations. Coordinated navigation awareness becomes more important during peak activity periods. Autumn represents another transition phase that commands respect among experienced lake users. Surface water begins cooling again, gradually reducing stratification. Full storms often intensify because temperature contrasts between air masses grow stronger. Some historically severe Great Lakes storms have occurred during late autumn, when warm water meets advancing cold air systems. Wind patterns during autumn can sustain strong wave development for extended periods. Because recreational activity remains common during early fall, people sometimes encounter conditions closer to winter severity than summer calm. Preparation practices typically adjust accordingly among seasoned mariners. Reduced daylight hours during autumn and winter influence safety considerations too. Navigation in darkness requires reliable lighting, instrumentation, and route familiarity. Cold temperatures combined with darkness increase fatigue risk for crews exposed to harsh conditions. Ecological changes accompany seasonal cycles as well. Fish migration patterns shift, influencing fishing activity locations. Algae blooms sometimes occur during warm periods, affecting water clarity and potentially altering shoreline conditions. While not always directly dangerous, these changes influence how people interact with the water. Infrastructure maintenance often follows seasonal rhythms. Some marinas close during winter, reducing available refuge points. Navigation aids such as buoys may be removed before ice formation and redeployed in spring. Awareness of which aids are operational at any given time helps avoid navigational confusion. Weather forecasting becomes especially important during transitional seasons. Monitoring marine-specific forecasts rather than general land forecasts improves accuracy because lake conditions differ from inland conditions. Many experienced boaters maintain multiple forecast sources for cross-verification. Climate variability is beginning to influence seasonal patterns. Some years experience reduced ice cover, while others see extensive freezing. Water level fluctuations also respond to precipitation trends and evaporation rates. These evolving conditions require continuous monitoring by scientific agencies and maritime authorities. Search and rescue planning adapts seasonally. Equipment readiness, response protocols, and training scenarios adjust based on expected conditions. Cold water rescue training intensifies before spring boating seasons, while ice rescue readiness increases during winter months. Educational outreach often follows these seasonal shifts. Public safety campaigns emphasize cold water awareness in spring, storm preparedness in autumn, and ice safety in winter. Coordinated messaging helps reinforce awareness before risk peaks. Local communities surrounding the Great Lakes frequently maintain long-standing traditions tied to seasonal cycles. Ice fishing, seasonal shipping festivals, boating events, and environmental monitoring programs reflect the cultural importance of these waters. Cultural familiarity, however, does not eliminate physical risk. Technological monitoring continues improving seasonal understanding. Satellite imagery tracks ice cover changes. Buoy networks measure temperature profiles, wave conditions, and wind patterns. Data integration supports better forecasting and hazard communication. Environmental stewardship remains closely tied to seasonal awareness. Pollution runoff, shoreline erosion, and habitat protection efforts depend on understanding seasonal water movement patterns. These environmental efforts indirectly support human safety by maintaining navigable and predictable conditions. Psychological adaptation to seasonal change varies. Residents often develop intuitive awareness over years of observation. Visitors may lack that familiarity, making education and signage particularly important in tourist areas. Transportation logistics adjust seasonally as well. Commercial shipping schedules align with ice conditions. Ferry operations adapt routes and timing. Recreational charter services modify offerings based on expected weather stability. Medical preparedness factors into seasonal planning. Cold exposure treatment readiness, hypothermia awareness, and emergency response training all adapt to anticipated environmental conditions. Coordination between maritime authorities and medical services strengthens overall safety networks. Understanding seasonal extremes ultimately highlights a recurring theme. The Great Lakes are dynamic systems, not static bodies of water. Ice formation, thaw cycles, temperature layering, storm variability, and ecological changes all influence how safe or hazardous these waters may be at any given time. And as seasonal change becomes part of the overall picture, another historical layer begins to appear naturally. Over centuries, these lakes have accumulated a remarkable number of shipwrecks, many linked to the very conditions just described. That history provides practical lessons about navigation, weather awareness, and the enduring need for respect when operating on these vast freshwater seas. As seasonal change becomes part of the overall picture, another layer naturally begins to surface, and that layer sits quite literally beneath the water. The Great Lakes hold one of the highest concentrations of historic shipwrecks anywhere in the world. Thousands of vessels ranging from small wooden schooners to massive steel freighters now rest on lakebeds. This is not simply an interesting historical detail. It reflects how environmental conditions, geography, weather patterns, and human decision-making have combined over centuries to make these waters far more demanding than their calm surface sometimes suggests. The number alone is striking. Estimates vary, but historians and marine archaeologists generally place documented Great Lakes shipwrecks at over 6,000. Some are well mapped and studied, while others remain undiscovered. Cold freshwater preserves wrecks differently than saltwater oceans. Lower salinity slows corrosion and reduces biological activity that would otherwise break down wood and metal. As a result, many wrecks remain remarkably intact even after decades or centuries underwater. Divers often report seeing hulls, cargo, and even interior fittings preserved in ways rarely seen in marine environments. Geography played a major role in early maritime losses. Before modern navigation technology, sailors relied on landmarks, rudimentary charts, and basic instruments. The Great Lakes feature complex coastlines, shifting sandbars, rocky shoals, and narrow connecting channels. Fog, storms, and darkness frequently obscured visual cues. Groundings occurred when vessels unknowingly approached shallow areas or rocky outcrops. Once grounded, wave action often caused structural failure. Weather has historically been one of the most consistent contributing factors. Sudden storms, especially during autumn, have overwhelmed vessels caught far from safe harbour. Historical accounts describe wind shifts that intensified quickly, generating steep waves capable of damaging hulls or flooding cargo holds. Wooden ships of earlier centuries were particularly vulnerable to repeated wave impacts. Even later steel vessels sometimes succumbed when structural fatigue combined with severe weather. The infamous late autumn storm season holds particular significance. Warm lake water interacting with advancing cold air masses produces strong atmospheric instability. Some of the largest maritime disasters on the Great Lakes occurred during these seasonal transitions. Crews often underestimated how quickly conditions could escalate. Weather forecasting technology at the time provided limited advance warning, leaving captains to rely largely on experience and observation. Navigation technology has improved dramatically, yet shipwrecks did not stop entirely with modernization. Radar, GPS, electronic charts, and automated identification systems reduce risks substantially, but human error, mechanical failure, and extreme weather still occasionally produce incidents. Investigations typically highlight multiple contributing factors rather than a single cause. Commercial shipping pressure historically increased risk as well. During industrial expansion in the 19th and early 20th centuries, cargo demand grew rapidly. Iron ore, coal, grain, timber, and manufactured goods moved across the lakes in large volumes. Tight delivery schedules sometimes encouraged sailing in marginal conditions. While economic necessity drove these decisions, it occasionally resulted in vessels encountering storms they might otherwise have avoided. Structural ship design evolved partly in response to accumulated wreck experience. Early wooden schooners gave way to steel-hulled freighters, with reinforced bows, watertight compartments, and improved propulsion systems. These changes increased survivability, but they did not eliminate environmental challenges. Steep waves, icing conditions, and navigation hazards continued to demand careful seamanship. Certain regions of the lakes became known informally as shipwreck coastlines. Areas along Lake Superior, parts of Lake Huron's eastern shore, and several narrow connecting waterways accumulated particularly high numbers of wrecks. These zones often combine complex shoreline geography, strong prevailing winds, and heavy shipping traffic. Marine charts and navigational aids in these areas are now extensive, reflecting lessons learned over decades. Marine archaeology has become an active field in the Great Lakes. Researchers map wreck sites using sonar imaging, remotely operated vehicles, and diver surveys. These studies provide insights into ship construction techniques, cargo transport history, and environmental conditions at the time of sinking. Preservation in cold freshwater makes these sites valuable historical records. Legal protection frameworks now safeguard many wreck sites. Governments recognize both historical value and safety concerns associated with diving near fragile structures. Controlled access programs allow recreational divers to visit certain wrecks under regulated conditions. Educational outreach accompanies these programs to promote preservation awareness. Environmental impact from wrecks varies. Older wooden vessels generally pose minimal ecological risk today, while some modern wrecks containing fuel or hazardous cargo require monitoring. Cleanup operations and containment strategies form part of environmental management planning where necessary. Public awareness of shipwreck history has grown through museums, documentaries, and maritime heritage centres. Exhibits often highlight how environmental conditions contributed to maritime losses. Understanding these historical events reinforces modern safety education. Search and rescue evolution reflects accumulated experience. Early maritime response relied on nearby vessels or coastal communities. Modern operations involve coordinated Coast Guard units, advanced communication networks, aerial surveillance, and specialized rescue craft. These developments significantly reduce fatalities compared with earlier eras. Weather forecasting advancements represent another critical improvement. Satellite monitoring, computer modeling, and buoy networks provide detailed real-time data. Mariners now receive warnings earlier, allowing route adjustments or delayed departures when necessary. Communication technology also transformed safety outcomes. Radio systems enable immediate distress signaling. Satellite communication extends coverage across remote lake areas. Emergency locator beacons provide precise positioning information for rescue teams. Still, historical patterns continue informing current practices. Training programs reference past incidents to illustrate how small misjudgments can escalate under challenging conditions. Lessons from wreck investigations feed into updated navigation protocols and vessel design improvements. Recreational boating has expanded significantly over recent decades. Awareness of historical shipwreck concentrations helps guide safety messaging for non-commercial users, Even small craft operating in historically hazardous zones benefit from understanding environmental characteristics that contributed to past incidents. Diving tourism around shipwrecks has become popular. Clear freshwater visibility and preserved structures attract enthusiasts. Safety protocols emphasize proper training, environmental respect, and awareness of changing lake conditions during dive operations. Cultural identity in Great Lakes communities often incorporates maritime history. Festivals, memorials, and educational programs acknowledge both economic importance and the human cost of maritime accidents. These cultural practices reinforce respect for the lake's power. Technological preservation methods continue improving. Digital mapping, 3D modelling, and archival documentation help maintain records even when physical structures deteriorate slowly over time. Researchers share findings internationally, contributing to broader maritime heritage understanding. Insurance and regulatory frameworks evolved partly in response to historical losses. Shipping companies now follow stricter safety standards, vessel inspection routines, and crew training requirements. Compliance monitoring helps maintain these standards. Environmental monitoring of wreck sites sometimes reveals ecological benefits. Artificial reef effects occur when structures provide habitat for fish and other aquatic organisms. While not originally intended, some wrecks contribute positively to local ecosystems. Legal jurisdiction across international borders adds complexity. The United States and Canada coordinate protection efforts, research permissions, and safety regulations. Shared governance ensures consistent preservation and operational standards. Educational institutions incorporate shipwreck studies into broader maritime science programs. Students examine hydrodynamics, meteorology, engineering, and human factors through historical case analysis. This interdisciplinary approach strengthens future maritime safety expertise. Public storytelling about shipwrecks often focuses on dramatic narratives, yet the underlying reality is usually practical. Weather patterns, structural limits, navigation challenges, and human decision-making combine to produce outcomes. Understanding those practical factors helps maintain realistic awareness rather than romanticize danger. Modern shipping continues benefiting from historical knowledge. Route planning, seasonal scheduling, vessel design, and crew training all incorporate lessons learned over generations. Continuous improvement remains central to maritime safety culture. Data integration technologies now combine historical incident databases with real-time environmental monitoring. Predictive models help identify higher-risk conditions, supporting proactive decision-making for both commercial and recreational operators. All of this historical perspective reinforces a consistent idea. The Great Lakes have long demonstrated ocean-level hazards despite being freshwater bodies. Shipwreck records provide tangible evidence of environmental forces interacting with human activity over time, and as that historical layer becomes clearer, attention naturally begins shifting toward another practical consideration tied to those same incidents. Depth, darkness, and underwater conditions significantly influence rescue operations and survival outcomes. Understanding how those factors affect modern safety becomes the next logical piece of the overall picture. As the long history of shipwrecks begins to make practical sense rather than just historical curiosity, another physical reality naturally comes into focus, and that reality is what lies below the surface. The Great Lakes are not only vast in area, they are also deep, in some places surprisingly so. That depth, combined with cold water, limited light penetration, and environmental conditions that shift quickly, directly affects how rescue operations unfold. It also influences survival time, detection probability, and the complexity of underwater search efforts. These factors rarely appear obvious from the shoreline, yet they quietly shape how emergencies develop and how difficult they can be to resolve. Depth varies widely across the lakes, but several basins rival coastal ocean shelf depths. Lake Superior, for example, reaches depths of over 400 meters. Other lakes contain deep troughs formed by glacial activity thousands of years ago. Those deep areas store cold water year-round. Temperature stratification keeps deeper layers consistently cold, even when surface temperatures rise seasonally. This persistent cold reservoir influences survival outcomes in immersion incidents. Cold water reduces survival time significantly. Hypothermia develops more rapidly in cold fresh water than many people expect, particularly when combined with wind exposure and physical fatigue. Even strong swimmers can lose effective muscle control within relatively short periods. This means that rescue timing becomes critical. The window for successful recovery without serious medical complications can be narrow. Darkness underwater complicates search operations. Freshwater clarity varies by location and season, but depth quickly reduces light penetration. Suspended sediments, biological material, and seasonal algae blooms further limit visibility. Divers conducting search missions often rely on artificial lighting, sonar imaging, and remotely operated vehicles. These tools improve effectiveness but require time, specialized training, and careful coordination. Surface conditions influence underwater visibility indirectly. Strong winds stir up sediments near shorelines, reducing clarity. Storm runoff from rivers introduces additional particulate matter. After heavy weather events, search teams frequently encounter reduced visibility, even in areas normally considered clear. Nighttime operations add another layer of difficulty. Darkness above the surface affects aerial search coordination, visual spotting, and navigation. Rescue teams use infrared imaging, radar, and high-intensity lighting to compensate, but those technologies have practical limits, especially in rough weather. Water temperature also affects equipment performance. Batteries discharge faster in cold conditions. Mechanical systems may require additional maintenance. Protective gear for rescue personnel must provide insulation without restricting mobility. These operational considerations influence response speed and effectiveness. Communication challenges sometimes arise in remote lake regions. While coastal areas near major cities benefit from strong communication infrastructure, more isolated sections may have limited signal coverage. Satellite communication helps bridge gaps, but equipment availability varies among recreational users. Depth affects recovery logistics as well. Salvage operations for sunken vessels or equipment require specialized lifting gear, precise positioning systems, and favorable weather windows. Historical shipwreck preservation demonstrates how difficult recovery can be once objects settle at significant depths. Buoyancy differences in freshwater compared with saltwater subtly influence rescue dynamics. Slightly reduced buoyancy means flotation devices remain essential for maintaining airway clearance. Rescue training incorporates these differences when planning retrieval techniques. Thermal layering influences diver safety. Divers entering cold, deep water require appropriate thermal protection. Exposure limits exist to prevent hypothermia among rescue personnel themselves. Rotational staffing ensures divers do not exceed safe exposure durations. Sound propagation underwater behaves differently in freshwater than saltwater, affecting acoustic search tools. Sonar remains highly effective, but calibration accounts for temperature gradients and density variations. Search planning incorporates these physical properties. Helicopter rescue operations often play a central role due to distance from shore. Hoist operations in cold, rough water require precise coordination between pilots, rescue swimmers, and onboard medical personnel. Training exercises simulate these conditions regularly. Medical response after rescue emphasizes rapid rewarming protocols, respiratory assessment, and cardiovascular monitoring. Cold shock, hypothermia, and aspiration risk require specialized treatment approaches. Hospitals near the lakes maintain readiness for such cases. Human factors remain significant. Panic responses during immersion reduce energy efficiency and accelerate heat loss. Training programs encourage controlled breathing, flotation posture maintenance, and signalling techniques to extend survival time. Environmental noise complicates detection. Wind, waves, and precipitation reduce auditory cues. Visual spotting becomes difficult when water surfaces are disturbed. Coordinated multi-platform searches combining aerial, surface, and underwater assets improve detection probability. Technology continues evolving. Autonomous underwater vehicles, enhanced sonar imaging, and improved thermal detection systems expand search capabilities. Adoption across rescue organizations varies based on funding and operational priorities. Historical incident analysis informs current rescue protocols. Lessons from past operations guide improvements in communication procedures, equipment standards, and training curricula. Continuous evaluation supports incremental safety gains. Public education contributes indirectly to rescue success. Awareness campaigns emphasizing flotation device use, trip planning, and emergency signaling reduce incident severity. Preventive measures often determine whether rescue becomes necessary at all. Environmental stewardship intersects with rescue logistics. Maintaining navigational aids, monitoring pollution levels, and managing shoreline development supports safer operating conditions overall. Collaborative efforts between environmental agencies and maritime authorities strengthen these outcomes. Seasonal preparedness remains important. Ice rescue training intensifies during winter months. Cold water immersion awareness campaigns peak in spring. Storm preparedness messaging increases in autumn. Aligning education with seasonal risk patterns enhances effectiveness. Community involvement plays a supportive role. Volunteer organizations, local boaters, and shoreline residents sometimes assist in initial response before professional teams arrive. Training outreach helps ensure such assistance enhances rather than complicates rescue efforts. Insurance and regulatory frameworks encourage adherence to safety standards. Vessel inspections, mandatory equipment requirements, and operator certification programs reduce incident likelihood. Compliance monitoring supports consistent safety culture. Research institutions continue studying cold water survival, underwater visibility dynamics, and rescue technology effectiveness. Findings inform policy updates, equipment design improvements, and training modifications. International cooperation between bordering countries supports coordinated response capability. Shared waters require compatible communication systems, joint exercises, and standardized protocols. These collaborative efforts improve cross-border rescue efficiency. All of these considerations reinforce a consistent point. Depth and darkness do not merely add physical complexity. They shape survival timelines, influence rescue logistics, and demand specialized preparation from both professionals and recreational water users. And once the operational challenges of depth become clearer, another human-centered factor begins to stand out. Familiar landscapes sometimes encourage overconfidence. People who live near these lakes often feel comfortable around them, and that comfort, while understandable, can occasionally reduce perceived risk. Understanding how familiarity influences behavior becomes the next piece of the broader picture. As the physical realities of depth, cold water, and rescue difficulty begin to settle into a clearer picture, attention naturally shifts towards something less visible, but just as influential. That factor is human perception. Not the water itself, not the weather, not geography, but how people think about the environment around them. Familiar landscapes tend to lower psychological defenses. When something feels known, routine, or part of everyday life, the instinct to prepare carefully often softens. Around the Great Lakes, this dynamic appears frequently because millions of people live near these waters, visit them regularly, and associate them with recreation, relaxation, and normal daily experience rather than maritime risk. Familiarity has many benefits. Local knowledge improves navigation awareness, seasonal understanding, and environmental respect. However, familiarity can also produce subtle overconfidence. This usually does not appear as deliberate risk-taking. It shows up in small choices. Skipping a second weather check, leaving flotation devices stowed rather than worn, assuming a short trip offshore will remain manageable because it usually does. Each individual decision seems minor, but together they can reduce safety margins. Psychologists sometimes refer to this pattern as normalization of risk. When people repeatedly encounter a potentially hazardous situation without negative outcomes, the perceived risk declines. A boater who has crossed a particular stretch of lake dozens of times without incident may gradually treat it as routine, even though conditions could change dramatically on any given day. The environment has not become safer, but perception has shifted. Residential proximity contributes to this effect. People who grow up near the Great Lakes often integrate the water into their identity. Beaches, harbours, and shoreline parks become part of daily scenery. That closeness fosters comfort, yet it can also reduce the sense of caution visitors might naturally maintain. Someone encountering the lakes for the first time may approach with heightened awareness simply because the environment feels unfamiliar. Seasonal repetition strengthens the pattern. Summer boating, autumn fishing, winter ice recreation, and spring shoreline activities create yearly cycles of interaction. When each season passes without major incident, confidence grows. That confidence is understandable, but it sometimes masks the variability inherent in large freshwater systems. Weather perception illustrates this clearly. Residents may develop informal expectations about typical conditions based on past experience. While experiential knowledge can be valuable, weather patterns shift year to year. Climate variability introduces additional uncertainty. Relying solely on memory rather than current forecasts occasionally leads to underestimating emerging conditions. Technological familiarity contributes as well. Modern navigation apps, GPS devices, and weather alerts provide impressive support. Regular users grow comfortable with these tools, yet technology can fail. Batteries discharge, signals weaken, software glitches occur. Over-reliance without backup planning reduces resilience when unexpected problems arise. Recreational culture reinforces relaxed attitudes. Advertising imagery often presents lakes as tranquil vacation destinations. Calm water, sunsets, fishing boats, and shoreline cottages dominate public perception. These images are not inaccurate, but they rarely show storm conditions, cold water hazards, or complex navigation environments. Public perception becomes weighted toward calm scenarios. Social dynamics play a role too. When groups of friends or family share similar familiarity, collective confidence can increase. If everyone assumes conditions are safe, dissenting caution sometimes feels unnecessary. Group consensus occasionally overrides individual hesitation, especially during recreational outings where relaxation is the goal. Experience level creates an interesting contrast. Professional mariners operating on the Great Lakes often display heightened caution precisely because of their experience. They have encountered storms, visibility loss, mechanical issues, and seasonal extremes. That experience reinforces respect. Recreational users with moderate experience but fewer extreme encounters may feel confident without having faced the full range of conditions. Historical awareness influences perception as well. People familiar with shipwreck history, rescue operations, or documented incidents often maintain greater caution. Educational outreach, highlighting past events, helps align perception with environmental reality without creating unnecessary fear. Economic dependence on the lakes shapes attitudes too. Commercial fishermen, shipping crews, harbour workers, and tourism operators interact with the lakes professionally. Their livelihood depends on safe operation. Training, regulation, and experience foster structured safety practices. Casual users sometimes lack equivalent structured preparation. Physical proximity to shorelines can produce a false sense of accessibility. Seeing land, buildings, or familiar landmarks creates comfort. Yet distance perception over water is often misleading. A shoreline that looks close may require substantial travel time to reach. particularly in rough conditions or limited visibility. Cold water awareness again intersects with perception. Many residents intellectually know the lakes remain cold much of the year, yet air temperature strongly influences comfort expectations. Warm summer days encourage lighter clothing and relaxed preparation, even though water temperatures may remain low enough to pose risk. Emergency preparedness behaviours reflect perception shifts. Carrying safety equipment differs from actively preparing to use it. Life jackets stored under seats provide less protection than those worn. Emergency radios turned off save battery life but reduce readiness. Small adjustments in perception influence these decisions. Education campaigns increasingly address this psychological dimension. Messaging emphasizes consistent preparation regardless of familiarity. Safety checklists, flotation device promotion, and weather awareness reminders aim to counter normalization of risk. Community leadership helps reinforce safe habits. Sailing clubs, marina operators, and experienced boaters often model cautious practices publicly. Observing respected community members prioritize safety encourages broader adoption. Incident investigations frequently identify perception factors. Reports often note that conditions appeared manageable initially, leading to delayed precautionary action. Understanding these patterns informs updated training recommendations. Technological data analysis contributes insights. Tracking patterns in boating incidents, rescue calls, and weather conditions helps identify common decision points where perception influenced outcomes. This evidence-based approach supports targeted education. Cultural storytelling also shapes attitudes. Stories emphasizing safe return, preparedness, and respect for conditions help balance narratives that focus solely on recreation. Maritime heritage centers increasingly incorporate safety education into historical exhibits. Youth education programs play a preventive role. Teaching water safety, weather awareness, and navigation basics early builds lifelong habits. Schools near the lake sometimes integrate environmental science with safety training. Insurance incentives occasionally encourage safer behaviour. Reduced premiums for vessels equipped with certain safety features or operated by certified individuals reinforce structured preparation. Technological innovation continues improving accessibility to information. Real-time buoy data, satellite weather imagery, and automated alerts provide valuable awareness tools. Ensuring users interpret this information correctly remains important. Climate change discussions add another perception layer. As environmental patterns shift, past experience becomes a less reliable predictor of future conditions. Maintaining adaptability in safety practices becomes increasingly relevant. Environmental stewardship and safety awareness often intersect. Individuals engaged in shoreline conservation, water quality monitoring, or ecological education tend to develop deeper appreciation for environmental dynamics, including safety implications. Ultimately, familiarity is not inherently negative. It builds connection, appreciation, and local expertise. The key lies in balancing comfort with continuous awareness that large freshwater systems remain dynamic and sometimes unpredictable. And once the influence of human perception becomes clearer, another practical factor naturally follows. Distance and communication limitations can affect how quickly assistance arrives when something goes wrong. Understanding isolation factors, both geographic and technological, adds another dimension to how safety is managed on these expansive inland waters. Once familiarity and perception settle into place as part of the overall picture, another practical reality naturally becomes more noticeable, and that reality involves isolation. Even though the Great Lakes are surrounded by cities, towns, ports, and recreational areas, large portions of these waters remain surprisingly remote once you move away from shore. Distance, communication reliability, weather interference, and logistical constraints all shape how quickly assistance can arrive if something goes wrong. Isolation does not always mean being alone visually. It often means being far enough from immediate support that response timing becomes a significant factor. Distance is the most straightforward part. The Great Lakes cover enormous surface areas. Travelling several kilometres offshore can happen quickly, especially with modern recreational boats capable of moderate speeds. Yet returning the same distance under deteriorating weather conditions may take considerably longer. Mechanical issues, fuel limitations, or sudden storms can turn what seemed like a short outing into an extended exposure situation. Response times depend heavily on location. Near major ports such as Chicago, Toronto, Cleveland or Duluth, Coast Guard stations, Marine Police units and harbour patrols maintain active readiness. These units can often respond quickly. In more remote northern sections, particularly along parts of Lake Superior or northern Lake Huron, response distances increase. Helicopters, rescue vessels and coordination teams may need additional time to reach a distressed vessel. Weather complicates response logistics further. Strong winds, fog, lightning, heavy precipitation, or winter ice conditions all influence how safely rescue teams can operate. Helicopter hoists require stable wind conditions. Surface vessels must navigate the same rough water as those needing assistance. Safety of rescue personnel remains a priority, which occasionally affects response timing. Communication reliability varies across the lakes. Marine VHF radio remains a primary emergency communication method. Coverage is generally good near populated shorelines, but can weaken farther offshore or near complex terrain features. Portable radios help, but antenna height, battery condition, and environmental interference influence performance. Cellular coverage provides another communication layer, but signal strength diminishes offshore. Modern smartphones may connect intermittently depending on tower proximity. Relying solely on cellular communication for safety planning carries risk. Satellite communication devices offer broader coverage but require dedicated equipment. Emergency locator beacons have become increasingly common among experienced boaters. These devices transmit distress signals via satellite networks, providing location data to rescue coordination centres. Their effectiveness depends on proper registration, battery maintenance, and correct activation procedures. Isolation also affects decision-making before emergencies occur. Knowing that assistance may take time encourages more conservative planning. Checking weather forecasts carefully, informing others of travel plans, carrying redundant navigation tools, and maintaining safety equipment readiness all reduce vulnerability. Fuel planning illustrates this principle clearly. On smaller lakes, refueling points are usually nearby. On the Great Lakes, distances between marinas can be substantial. Running low on fuel far from shore creates avoidable risk. Conservative fuel reserves form part of prudent trip preparation. Mechanical reliability becomes more critical in isolated areas. Regular maintenance, spare parts availability, and basic repair knowledge help prevent minor issues from escalating. Commercial operators typically follow strict maintenance schedules. Recreational users benefit from similar attention to vessel condition. Environmental exposure increases with distance from shelter. Sun exposure, wind chill, and precipitation affect crew endurance. Adequate clothing, hydration supplies, and protective gear help maintain physical readiness during extended outings. Navigation redundancy supports safety in isolation. Electronic chart plotters provide precision, but traditional charts, compasses, and visual navigation skills remain valuable backups. Equipment failure rarely announces itself in advance. Search patterns during rescue operations depend partly on last known position information. Clear float plans shared with family, friends, or marina operators improve response accuracy. Uncertainty about departure time, intended route, or destination complicates search coordination. Commercial shipping sometimes assists in emergencies when nearby. Maritime tradition encourages mutual assistance, and large vessels may provide initial support while formal rescue teams mobilize. Awareness of shipping traffic can therefore offer indirect safety benefits. Nighttime isolation introduces additional considerations. Darkness reduces visual detection capability. Lighting systems, reflective materials, and emergency signaling devices improve visibility to rescuers. Proper vessel lighting also helps prevent collisions. Seasonal isolation patterns differ. Winter ice reduces recreational traffic in some areas, meaning fewer nearby vessels capable of offering immediate assistance. Spring and autumn shoulder seasons may also see reduced activity compared with peak summer months. Environmental monitoring stations such as weather buoys contribute indirectly to safety. Real-time data helps boaters anticipate conditions, but physical distance from these stations still requires individual preparedness. International border proximity adds procedural complexity in certain areas. Cross-border rescue coordination functions well due to established agreements, yet awareness of jurisdictional boundaries can assist communication clarity during emergencies. Psychological factors influence perceived isolation. Being unable to see land, encountering fog, or losing communication signal may increase stress. Training that emphasizes calm assessment and structured response improves resilience under such conditions. Technological advancement continues reducing isolation effects. Improved satellite coverage, compact emergency beacons, and digital weather data access expand awareness. Adoption among recreational users remains uneven, making education important. Community networks support safety as well. Sailing clubs, fishing associations, and marina communities often share information informally. Peer communication helps identify emerging hazards, equipment recommendations, and best practices. Environmental stewardship initiatives sometimes enhance safety indirectly. Shoreline conservation, navigational aid maintenance, and pollution monitoring support clearer operating conditions. Cooperative efforts between agencies and communities strengthen these outcomes. Historical incident analysis consistently highlights isolation as a contributing factor. Delayed communication, uncertain positioning, and challenging weather conditions often combine. Lessons learned inform updated safety messaging. Economic considerations influence response infrastructure placement. High-traffic regions receive more concentrated resources. Remote areas depend more heavily on regional coordination. Awareness of these patterns informs trip planning decisions. Training programs increasingly incorporate isolation scenarios. Simulation exercises teach communication protocols, emergency equipment use, and decision-making under delayed assistance conditions. Such preparation improves real-world outcomes. Personal preparedness ultimately bridges the gap between environmental reality and safety. Carrying appropriate equipment, understanding communication options, and respecting distance all reduce risk. And once isolation factors become part of the broader understanding, another subtle but important aspect begins to emerge. Freshwater itself affects human buoyancy and survival characteristics differently than saltwater environments. That ecological difference, while not always obvious, plays a role in how incidents unfold on these lakes. As distance, communication limits, and response timing begin to frame how emergencies unfold on these lakes, another factor becomes relevant, and it sits quietly within the water itself. Freshwater behaves slightly differently from saltwater in ways that directly influence human survival, vessel performance, and rescue dynamics. The differences are subtle enough that many people never consciously notice them, yet when conditions become difficult, those small physical distinctions can shape outcomes in very practical ways. The most commonly discussed difference involves buoyancy. Salt water contains dissolved salts and minerals that increase its density. Higher density means objects, including the human body, float slightly more easily. Fresh water, by comparison, has lower density. The difference is not dramatic enough to be obvious during casual swimming, but in challenging conditions it becomes meaningful. A tired swimmer floating in salt water often finds maintaining airway position marginally easier than in fresh water. On the Great Lakes, that small reduction in buoyant support means flotation devices become even more important for energy conservation. Human body composition also interacts with buoyancy. body fat provides natural flotation, while muscle tissue is denser. Individuals with lower body fat sometimes notice they sink slightly more easily, particularly in fresh water. Clothing and gear add further variables. Heavy clothing becomes waterlogged, reducing buoyancy and increasing drag. This is one reason safety training emphasizes appropriate flotation equipment, rather than relying on swimming ability alone. Cold fresh water amplifies buoyancy challenges. When the body experiences cold shock, breathing control decreases. Rapid breathing, muscle tension, and reduced coordination increase energy expenditure. Combined with slightly lower buoyant support, fatigue develops faster than many people expect. Life jackets compensate for both buoyancy loss and reduced muscle control, keeping the airway above water even when active swimming becomes difficult. Ecological conditions also influence water clarity, which affects survival and rescue dynamics. Freshwater lakes often experience seasonal algae blooms, sediment runoff, and biological activity that change visibility. Clear water improves detection of individuals in distress, while murky conditions reduce visual spotting range. Search teams adjust techniques accordingly, using sonar or aerial imaging when visual detection becomes unreliable. Temperature layering, mentioned earlier in the context of seasonal cycles, also affects survival. Freshwater stratification creates distinct thermal layers. Surface water may feel relatively comfortable while deeper water remains cold. Sudden immersion, especially during capsizing incidents, exposes individuals to deeper cold layers quickly. That temperature gradient influences both physiological response and survival time. Water chemistry differences between freshwater and saltwater influence skin response, hydration dynamics, and equipment corrosion. Freshwater does not cause the same salt-related dehydration effects on skin, but prolonged immersion still leads to heat loss and skin softening. Rescue personnel sometimes note that extended freshwater immersion produces distinct physiological stress patterns compared with ocean exposure. Aquatic vegetation adds another ecological dimension. Nearshore areas often contain submerged plants, reeds, or algae mats. These do not usually present severe hazards, but in low visibility or panic situations, entanglement risk exists. Kayakers, swimmers, and small craft operators benefit from awareness of vegetation zones when planning routes. Invasive species have altered Great Lakes ecology significantly over recent decades. Zebra mussels and quagga mussels, for example, filter water extensively, increasing clarity in some regions. Clearer water might appear beneficial for navigation and recreation, yet it also allows sunlight to penetrate deeper, changing plant growth patterns and ecosystem balance. These ecological shifts indirectly influence water conditions, including shoreline stability and habitat distribution. Fish populations influence human interaction patterns too. Commercial fishing, recreational angling, and ecological monitoring activities increase traffic in certain areas. Awareness of fishing zones helps reduce conflict between recreational boaters and professional operators. Waterborne microorganisms rarely present immediate survival threats in immersion scenarios, but they influence long-term water quality management. Monitoring programs track bacterial levels near beaches and harbours, ensuring public health safety for recreational users. Salinity absence affects corrosion patterns on vessels. Fresh water is generally less corrosive than salt water, which extends vessel lifespan. However, reduced corrosion does not eliminate structural stress from waves, ice, or temperature cycles. Maintenance remains essential for safety. Sound propagation differs slightly between freshwater and saltwater environments. Acoustic communication devices, sonar equipment, and underwater detection systems account for these differences during calibration. Rescue operations benefit from accurate acoustic modelling when locating submerged objects or individuals. Ice formation patterns reflect freshwater characteristics. Saltwater freezes at lower temperatures, while freshwater ice forms more readily under freezing conditions. This seasonal ice cover influences navigation, ecological cycles, and recreational activity patterns. Hydration considerations sometimes surprise individuals immersed in freshwater. While saltwater ingestion can worsen dehydration, freshwater immersion still carries risks if swallowed excessively, including electrolyte imbalance. Rescue training emphasizes preventing unnecessary ingestion and rapid medical evaluation after prolonged immersion. Water pressure dynamics at depth differ slightly because of density variations. Divers operating in freshwater environments adjust buoyancy control systems accordingly. Rescue divers working on the Great Lakes train specifically for these conditions. Thermal conductivity plays a major role in survival. Water conducts heat away from the body much faster than air. Freshwater's thermal properties ensure that even moderate temperatures can lead to significant heat loss during extended immersion. Protective clothing, flotation devices, and prompt rescue coordination mitigate this risk. Ecological monitoring programs provide valuable real-time data. Temperature sensors, water chemistry analysis, and biological surveys inform both environmental protection and public safety planning. These data streams support forecasting models that improve hazard prediction. Weather interaction with freshwater surfaces differs from saltwater interactions in subtle ways. Evaporation rates, humidity generation, and cloud formation processes respond to freshwater characteristics. These atmospheric interactions contribute to fog formation, storm development, and seasonal precipitation patterns. Public health agencies monitor harmful algal blooms carefully. Certain blooms produce toxins affecting humans and animals. Beach advisories sometimes result from these ecological events. While not directly related to buoyancy or immediate survival, awareness helps avoid secondary health risks. Freshwater ecosystems support diverse wildlife. Birds, fish, amphibians, and plant communities all interact with human activity. Responsible boating practices reduce environmental disturbance while maintaining safety. Sediment transport patterns influence shoreline stability. Wave action redistributes sand and silt, affecting beach conditions. Changes in sediment distribution sometimes alter current patterns, navigation hazards, or harbour accessibility. Nutrient cycles within freshwater systems affect biological productivity. Agricultural runoff, urban development, and natural processes all contribute. Environmental management efforts aim to maintain ecological balance, indirectly supporting safe recreational conditions. Visibility underwater affects diver safety. Clear freshwater can create illusions of depth or distance, affecting orientation. Training programs emphasize instrument reliance alongside visual cues. Thermal comfort perception differs between freshwater and saltwater swimmers. Some individuals report freshwater feeling colder at equivalent temperatures. This perception may relate to density, evaporation patterns, or psychological familiarity. Search and rescue planning integrates ecological data. Understanding water temperature, clarity, current patterns, and biological activity improves predictive modelling for incident response. Climate variability continues influencing freshwater ecological conditions. Changing precipitation patterns, temperature trends, and invasive species dynamics all shape future water behaviour. Continuous monitoring supports adaptive safety strategies. Community education increasingly includes ecological awareness. Understanding how environmental factors influence safety encourages responsible lake use. Outreach programs often combine environmental stewardship with safety training. Technological advancements improve ecological monitoring. Satellite imagery, automated sensor networks, and data integration platforms enhance situational awareness for both environmental agencies and maritime operators. Freshwater research institutions collaborate internationally. Findings from the Great Lakes inform freshwater management worldwide. Safety insights derived from these studies benefit other large lake regions. Economic activity remains closely tied to ecological conditions. Fishing industries, tourism, shipping, and environmental conservation efforts all depend on maintaining healthy freshwater systems. personal preparation remains the most direct safety factor. Flotation devices, weather awareness, communication equipment, and route planning account for ecological realities effectively. Understanding freshwater ecological conditions ultimately reinforces a broader pattern. Small physical differences influence survival, navigation, and rescue outcomes more than many people realize. Awareness of those differences supports better preparation without requiring dramatic lifestyle changes. And once the ecological dimension becomes clearer, another human-centered aspect naturally follows. Perception, memory, and psychological interpretation of time spent on the water influence how people judge risk, respond to changing conditions, and recall past experiences. That psychological layer adds further depth to understanding how individuals interact with these expansive freshwater environments. As ecological conditions start to make sense in practical terms, another layer naturally comes into view, and that layer involves how people interpret the environment around them rather than the environment itself. The Great Lakes do not usually look intimidating in the same way oceans often do. There are no tides rising dramatically along beaches, no obvious salt smell in the air, no constant surf noise suggesting power. Instead, many shorelines look calm, familiar, even domestic. Houses, parks, marinas, and walking paths often sit right next to the water. That visual familiarity shapes psychological perception in ways that influence behavior, preparation, and sometimes risk assessment. One of the strongest influences is simple categorization. People grow up learning that oceans are large, powerful, and potentially dangerous. Lakes are usually presented as recreational spaces. Swimming lessons, fishing trips, summer camps, and holiday cabins reinforce this idea. When a body of water carries the label lake, many people subconsciously assign it a lower risk category, even when its physical characteristics match those of a small sea. The Great Lakes fall directly into that psychological gap. Visual scale can be deceptive as well. From many shoreline locations, the opposite shore is not visible, yet the environment still feels enclosed because maps, local knowledge, and cultural framing all emphasize that it is a lake. This combination allows the brain to register vast open water while still maintaining a sense of containment. That containment perception tends to reduce perceived urgency around safety precautions. Routine exposure strengthens this effect. Residents living near these lakes often see them daily. Morning commutes pass along shorelines. Weekend walks include waterfront views. Recreational outings become normal social activities. Repetition reduces novelty, and reduced novelty lowers perceived risk. This process happens gradually and without conscious intention. Memory also plays a role. People tend to remember calm, pleasant experiences more vividly than routine precautionary measures. A successful day of boating in mild weather reinforces confidence. Safety steps taken during that outing may fade from memory faster than the enjoyment itself. Over time, positive experiences accumulate while precautionary behaviours become background habits that sometimes get skipped. Social reinforcement contributes further. When friends, family members, or community groups treat lake activity casually, individuals often align with that collective attitude. Safety equipment may still be present, but visible emphasis decreases. Cultural norms develop around acceptable preparation levels, and those norms can drift toward convenience rather than caution. Environmental aesthetics influence perception too. Clear freshwater, sandy beaches, tree-lined shores, and relatively gentle wave sounds create a welcoming atmosphere. People associate these sensory cues with relaxation. Harsh ocean imagery, by contrast, often includes crashing surf, salt spray, and rugged coastlines. Sensory differences shape emotional responses before rational analysis even begins. Distance perception across water tends to be unreliable. Landmarks appear closer than they actually are due to lack of intermediate reference points. Someone looking across open lake water may assume shore is reachable quickly, even when conditions would make that return difficult. This visual compression contributes to underestimation of travel time and exposure duration. Weather perception follows a similar pattern. Calm mornings frequently occur on the Great Lakes, particularly in summer. These calm starts can create expectations of stable conditions. When weather changes later in the day, it may feel unexpected, even though forecasts indicated potential shifts. Experience with smaller lakes reinforces the expectation that calm conditions persist longer. Another psychological factor involves control illusion. Familiar environments give people a sense of mastery. Knowing local marinas, recognizing shoreline landmarks, or having completed similar trips before creates confidence. That confidence can be helpful, but it sometimes reduces attention to changing variables such as wind direction, water temperature, or visibility trends. Technological reassurance adds another dimension. Navigation apps, weather notifications, and communication devices provide valuable information. Regular use builds trust. However, reliance on technology can create a sense that unexpected problems will always be manageable, because information is readily available. When devices fail or signals weaken, adjustment can be slower than expected. Recreational framing of lake environments influences risk tolerance. Activities like swimming, paddleboarding, sailing, and fishing are marketed as relaxing pastimes. That framing encourages participation, which is positive, but it sometimes downplays environmental variability. Balanced messaging that includes both enjoyment and preparedness tends to produce safer outcomes. Childhood experience strongly shapes adult perception. Many people first encounter lakes during family vacations or camp programs focused on fun rather than hazard awareness. Those early associations persist. Even later education about large lake risks may not fully override those early emotional connections. Language itself contributes. Terms like beach day, lake house, or dock time emphasize leisure. Rarely do everyday conversations refer to these waters as inland seas, even though physically that description often fits better. Terminology subtly guides expectations. Media representation also plays a role. News coverage of ocean storms receives significant attention. Great Lakes weather events receive less international coverage, even when severe. Reduced visibility in media reinforces the perception that lake hazards are less significant. Cognitive bias, known as optimism bias, often appears in recreational settings. People acknowledge general risk but believe negative outcomes are unlikely for them personally. This bias affects decisions about life jacket use, weather monitoring, and distance planning. Time perception interacts with risk perception. When people feel relaxed, time often seems to pass quickly. A short outing may extend longer than planned without conscious notice. Reduced attention to time can influence fuel consumption, daylight availability, and weather exposure. Familiar sounds also shape comfort levels. Gentle wave lapping, distant boat engines, and shoreline activity create a sense of normalcy. In contrast, the constant roar of ocean surf often signals energy and potential hazard. Acoustic cues therefore influence emotional interpretation. Community education programs increasingly address psychological perception directly. Rather than focusing only on technical safety information, they emphasize awareness of how familiarity shapes decision-making. Understanding cognitive patterns helps individuals maintain balanced caution. Maritime professionals working regularly on these lakes often develop a different psychological relationship. Experience with storms, cold exposure, and navigation challenges reinforces respect. Their attitudes sometimes contrast with casual recreational users, highlighting how direct experience shapes perception. Seasonal variation affects perception as well. Summer crowds reinforce the image of safe recreational space. Winter isolation or storm conditions remind residents of environmental power. Public messaging often shifts seasonally to maintain balanced awareness. Environmental signage near beaches and marinas has evolved to reflect psychological insights. Clear, direct language combined with visual symbols improves comprehension and retention. Messaging avoids alarmism while still conveying realistic risk. Technological tools now incorporate behavioral design elements. Weather apps highlight sudden change risks. Navigation systems display proximity alerts. These features aim to counteract complacency without overwhelming users. Educational outreach through schools, community groups, and boating organizations continues expanding. Early exposure to balanced safety messaging helps align perception with environmental reality over time. Tourism industries increasingly integrate safety messaging into promotional materials. Visitors unfamiliar with the lakes benefit from guidance on weather awareness, flotation device use, and distance planning. Local storytelling traditions often include historical storm accounts or maritime incidents. These narratives maintain cultural memory of environmental power without discouraging recreation. Balanced storytelling supports realistic perception. Research in environmental psychology continues examining how people interpret water landscapes. Findings inform safety campaigns, infrastructure design, and communication strategies. Ultimately, perception does not need to shift toward fear. Respect combined with enjoyment creates sustainable interaction with these waters. Recognizing that familiarity can sometimes soften caution simply encourages small adjustments in preparation and awareness. And as psychological perception settles into place alongside ecological, geographic, and historical factors, the broader picture of how people learn from real experiences begins to take shape, particularly through stories and lessons passed down by those who have encountered challenging conditions firsthand. As psychological perception becomes part of the overall understanding, another perspective begins to matter, and that perspective comes from people who have actually experienced difficult situations on these lakes and lived to talk about them. Survivor accounts do not usually sound dramatic or heroic when told in calm hindsight. They tend to focus on small details, small decisions, and subtle environmental cues that only became meaningful after the fact. Those experiences quietly shape how seasoned boaters, fishermen, sailors, rescue crews, and even regular swimmers approach the Great Lakes over time. One consistent lesson that appears again and again involves preparation before departure rather than reaction after conditions change. Many survivors describe situations where everything seemed manageable at first. Weather forecasts looked acceptable, equipment appeared functional, and plans seemed routine. The turning point often came not from a single catastrophic event, but from several minor factors aligning. A slightly stronger wind than expected, a small navigation error, a mechanical issue that would normally be trivial, combined with distance from shore or dropping visibility. People who had extra fuel, functioning communication equipment, flotation devices already worn, or contingency routes planned consistently reported better outcomes. Weather awareness stands out as another recurring theme. Survivors often mention that they checked the forecast once but did not monitor updates continuously. The Great Lakes environment rewards ongoing observation. Wind direction changes, cloud development, barometric pressure trends, and even subtle water texture differences can signal shifts before official warnings update. Experienced lake users learn to treat weather information as dynamic, rather than fixed at departure time. Cold water exposure appears frequently in survivor narratives. Many individuals who entered the water unexpectedly describe the initial shock as far more intense than anticipated. Controlled breathing becomes difficult immediately. Muscle coordination drops quickly. Those wearing flotation devices report that simply staying afloat without needing to swim aggressively allowed them to regain breathing control. Those without flotation support often describe rapid fatigue, even if they considered themselves strong swimmers. Another lesson involves time perception during emergencies. Survivors frequently note that events seemed both fast and slow at the same time. Minutes felt extended while decision-making windows shrank. This altered perception sometimes delayed responses because individuals believed they had more time than they actually did. Training programs now emphasize recognizing that subjective time perception changes under stress, encouraging early action rather than delayed evaluation. Communication preparation consistently appears in positive outcome stories. Having a marine radio accessible rather than stored away, knowing emergency channel procedures, carrying charged backup communication devices, and informing someone on land about travel plans all improved response speed. Survivors often credit these simple preparations more than any dramatic rescue maneuver. Distance planning also surfaces repeatedly. Many individuals underestimated how far offshore they had travelled. Visual cues across large water surfaces compress distance perception. Survivors frequently report realising the true distance only after conditions worsened. Conservative route planning, fuel reserves, and time buffers became part of their future habits after such experiences. Equipment familiarity matters as much as equipment presence. Several accounts describe situations where safety gear existed but was unfamiliar. Emergency beacons not previously tested, radios with unclear operation steps, or life jackets stored in hard-to-reach compartments delayed response. Regular practice with safety equipment significantly improves reaction speed under stress. Lighting conditions appear in some accounts as well. Late-day outings sometimes extended into dusk unexpectedly. Reduced visibility complicated navigation, especially when weather changed simultaneously. Survivors often emphasize planning daylight margins generously, rather than assuming quick returns. Psychological factors emerge strongly in retrospective accounts. Initial denial that conditions were worsening delayed precautionary action in some cases. People expected situations to stabilize because previous outings had been uneventful. Recognizing early warning signs and acting conservatively becomes a habit many survivors adopt afterward. Group dynamics also influence outcomes. Some survivors recall hesitating to suggest turning back because others appeared comfortable. Social pressure, even subtle, can delay safety decisions. Experienced groups often designate a clear decision maker or agree in advance that any member can call for caution without debate. Navigation awareness is another repeated theme. Electronic navigation tools help greatly, but survivors often mention cross-checking digital information with visual observation, charts, and compass headings. Redundancy reduces reliance on any single system. Fatigue management becomes important during longer outings. Survivors sometimes describe how gradual tiredness reduced attention to changing conditions. Hydration, nutrition, rest breaks, and crew rotation support sustained alertness. Rescue professionals frequently share similar lessons from their perspective. They note that early distress calls almost always produce better outcomes than delayed ones. People sometimes hesitate to call for assistance because they believe the situation may resolve. Rescue teams consistently prefer early notification even if assistance ultimately proves unnecessary. Historical survivors from commercial shipping provide additional insight. Large vessel crews emphasize teamwork, structured communication, and strict adherence to safety protocols. Their experiences demonstrate how routine discipline prevents small issues from escalating. Recreational fishermen offer another perspective. Many spend long hours offshore in varying weather. Experienced anglers often monitor water temperature, wind direction, and cloud patterns closely. They develop intuitive awareness through repeated exposure while still relying on formal forecasts. Kayakers and small craft users highlight clothing preparation, thermal protection, waterproof gear, and flotation devices significantly improve survival comfort. Lightweight craft respond quickly to waves and wind, making early weather awareness particularly important. Ice season survivors add further lessons. Individuals rescued from unstable ice frequently describe misjudging thickness or ignoring temperature fluctuations. Community education now emphasizes checking local ice reports rather than relying on visual appearance alone. Visibility reduction experiences reinforce instrument training. Survivors caught in fog often stress how quickly orientation can degrade without proper navigation tools. Even experienced boaters benefit from practicing instrument navigation before encountering actual low visibility conditions. Commercial divers and marine archaeologists working around shipwrecks contribute insights into underwater hazards. Cold exposure, limited visibility, and depth challenges require careful planning. Their procedures often mirror rescue team protocols. Environmental awareness emerges as a quiet but important theme. Observing bird activity, watercolor changes, wind scent shifts, and cloud formations provides early cues. Survivors frequently mention noticing such cues only after learning their significance through experience. Mental resilience also plays a role. Remaining calm enough to follow procedures, conserve energy, and communicate clearly improves outcomes. Panic tends to accelerate fatigue and impair judgment. Training programs increasingly include stress management components. Technology adoption continues evolving based on survivor input. Personal locator beacons, automatic flotation devices, digital weather alert systems, and improved navigation software all reflect lessons learned from past incidents. Insurance data analysis contributes additional understanding. Patterns in claims reveal common risk factors. These findings inform safety recommendations, equipment standards, and educational outreach. Community storytelling preserves experiential knowledge. Informal conversations at marinas, fishing docks, sailing clubs, and coastal communities pass down practical advice. These narratives complement formal training. Educational institutions incorporate survivor accounts into safety curricula. Real-world examples illustrate how theoretical knowledge applies in practice. Students often retain lessons more effectively when tied to actual experiences. Tourism operators increasingly integrate safety briefings based on survivor insights. Charter boat passengers receive clear guidance on flotation devices, weather awareness, and communication protocols before departure. Environmental stewardship intersects with survivor lessons too. Clean waterways, maintained navigation aids, and well-managed shorelines support safer operation. Community involvement in conservation indirectly enhances safety. Cross-border cooperation benefits from shared experience. The United States and Canada jointly analyse incidents, coordinate rescue training, and update regulations based on accumulated knowledge. Climate variability introduces new considerations. Changing ice cover patterns, shifting storm timing, and water level fluctuations require adaptive safety practices. Survivor experiences help identify emerging trends early. Medical response teams also learn from survivor outcomes. Treatment protocols for cold shock, hypothermia, and immersion-related stress evolve based on case analysis. Rapid rewarming techniques and post-rescue care continue improving. Personal habits often change permanently after close calls. Survivors frequently adopt stricter safety routines, carry additional equipment, and share their experiences publicly to help others avoid similar situations. The overall pattern that emerges from these accounts is not dramatic heroism, but consistent practicality. Small precautions, steady awareness, and willingness to act early tend to produce safer outcomes. The lakes themselves remain unchanged, but human interaction with them evolves through accumulated experience. And once those lived lessons begin shaping how people approach these waters, the broader perspective naturally moves toward what it means to coexist with such powerful yet accessible environments, particularly how respect, preparation, and awareness allow continued enjoyment without unnecessary risk. As those first-hand lessons settle in, a broader perspective begins to form almost naturally. The Great Lakes are not simply scenic backdrops, recreational playgrounds, or transportation corridors. They are vast freshwater systems shaped by geology, climate, ecology, and human history. They do not demand fear, but they do reward respect. That distinction matters because fear often discourages engagement, while respect encourages preparation, awareness, and thoughtful interaction. One of the most consistent realizations people arrive at after spending time on these lakes is how easily calm conditions can coexist with underlying complexity. A still morning surface may hide cold depths, changing weather patterns, or distant wave development. Familiar shorelines may create comfort while distance quietly expands offshore. These contrasts do not make the lakes hostile. They simply remind anyone interacting with them that appearance does not always reflect full environmental reality. Respect often begins with information. Weather awareness remains one of the simplest yet most effective safety practices. Checking marine forecasts, monitoring updates during outings, and recognizing early visual cues allow decisions to happen before conditions deteriorate. Forecasting technology continues improving, but interpretation still benefits from human attention and local knowledge. Equipment preparation forms another practical layer. Flotation devices, communication tools, navigation aids, thermal clothing, and emergency supplies do not need to feel excessive. They function best when integrated into routine practice, rather than treated as optional extras. Many experienced lake users eventually reach a point where preparation feels automatic, not burdensome. Distance awareness plays an equally important role. Large water surfaces create visual illusions. Land can appear close while actually requiring significant travel time. Conservative route planning, fuel reserves, and daylight considerations support safer decision-making without limiting enjoyment. Environmental understanding also strengthens confidence. Recognizing how cold water behaves, how waves develop, how fog forms, and how currents move near shorelines provides context that reduces surprise. Education does not eliminate risk entirely, but it transforms uncertainty into manageable knowledge. Community culture influences safety outcomes too. Marinas, sailing clubs, fishing communities, research institutions, and coastal towns often share knowledge informally. Conversations, local advisories, and shared experience build collective awareness. Participating in that culture encourages balanced attitudes toward both recreation and caution. Technology has become a valuable ally. Satellite weather data, GPS navigation, digital communication systems, and automated alerts provide unprecedented situational awareness. Used thoughtfully, these tools expand safety margins. Used casually without understanding limitations, they can foster overconfidence. Balanced use supports informed decisions. Environmental stewardship intersects naturally with safety. Clean water, maintained shorelines, protected habitats, and well-managed infrastructure all contribute to predictable conditions. Supporting conservation efforts indirectly enhances recreational and commercial safety. Seasonal awareness continues shaping interaction patterns. Ice formation, thaw cycles, storm seasons, and summer recreational peaks each introduce distinct considerations. Adapting preparation to seasonal conditions maintains consistency across the year. Education remains an ongoing process. Even experienced boaters, swimmers, and professionals encounter new situations. Continuous learning, refresher training, and openness to updated information help maintain readiness. Psychological awareness adds another dimension. Recognizing how familiarity influences perception allows individuals to maintain healthy caution without losing comfort. Awareness of cognitive biases supports balanced decision-making. Historical perspective provides context without alarm. Shipwreck records, survivor accounts, and maritime heritage remind people that these lakes have always required respect. At the same time, advances in technology, communication, and education have significantly improved safety outcomes compared with earlier eras. Rescue professionals, environmental scientists, and maritime operators all contribute to a broader safety ecosystem. Their work often happens quietly in the background, maintaining infrastructure, monitoring conditions, and responding when needed. Public awareness of these efforts reinforces appreciation for coordinated safety networks. Recreation remains an important part of life around the Great Lakes. Swimming, boating, sailing, fishing, wildlife observation, and shoreline tourism bring enjoyment to millions. Respectful preparation allows those activities to continue safely without diminishing their appeal. economic activity continues shaping regional development. Shipping routes, fisheries, tourism industries, and environmental research all depend on maintaining safe, navigable waters. Cooperation between nations, agencies, and communities supports these shared interests. Climate variability introduces evolving considerations. Water levels, ice cover duration, storm patterns, and ecological changes continue shifting gradually. Adaptive planning ensures safety practices remain aligned with current conditions. Future technological developments will likely expand monitoring capability further. Improved forecasting models, autonomous monitoring platforms, enhanced communication systems, and advanced rescue equipment continue emerging. Integrating these innovations thoughtfully supports ongoing safety improvements. Public messaging increasingly emphasizes balance. Enjoy the lakes, explore responsibly, prepare consistently. That approach avoids alarm while maintaining realism. Personal experience ultimately shapes individual relationships with these waters. Some people sail regularly, others fish occasionally, many simply enjoy shoreline views. Regardless of activity level, awareness of environmental dynamics enhances appreciation. Quiet respect tends to develop naturally over time. Not dramatic caution, not anxiety, simply consistent attentiveness. Checking conditions, wearing appropriate gear, planning routes carefully, and staying aware of surroundings become routine habits. And in that routine, something interesting often happens. The lakes remain beautiful, accessible, and inviting, yet they are no longer underestimated. They become understood as inland seas with their own character, rhythms, and requirements. If you have been listening while relaxing, travelling, or winding down, that broader understanding hopefully settles comfortably rather than urgently. The goal is not to change how you feel about water, only to deepen awareness slightly. Life beyond seen has always been about looking at familiar things a little more carefully, noticing details that usually stay in the background. The Great Lakes fit that idea well. Vast, familiar, sometimes calm, occasionally demanding, always worth understanding. Wherever you are listening from, whether near water or far inland, the relationship between humans and natural environments follows similar patterns. Awareness improves safety. Respect improves outcomes. Preparation supports confidence. And with that gentle perspective in place, the quiet surface of freshwater starts to look less ordinary, not more threatening, just more fully understood, which often makes future encounters with it feel calmer, not more tense.